1. Introduction. 1.1 Overview of simulating mouse clicks and keyboard presses. Simulating mouse clicks and keyboard presses in C using Linux allows developers to automate user interactions with the computer. This technique is particularly useful for tasks that require repetitive actions or for testing user interfaces. By simulating mouse clicks and keyboard presses, developers can save time and effort by automating these actions, making their programs more efficient and reliable. Simulating mouse clicks involves emulating the actions of a physical mouse, such as left-clicking, right-clicking, and middle-clicking. This can be done programmatically by sending appropriate signals to the operating system, which then interprets them as mouse events. Similarly, simulating keyboard presses involves emulating the actions of a physical keyboard, such as pressing individual keys or combinations of keys. One of the main benefits of simulating mouse clicks and keyboard presses is the ability to automate repetitive tasks. For example, if a developer needs to perform the same set of actions multiple times, they can write a program to simulate those actions instead of manually repeating them. This not only saves time but also reduces the risk of human error. Another benefit is the ability to test user interfaces more efficiently. Simulating user interactions allows developers to test different scenarios and edge cases without the need for manual input. This can be particularly useful when developing applications that have complex user interfaces or require extensive testing. Simulating mouse clicks and keyboard presses also provides a way to create virtual user interactions. This can be useful in scenarios where a program needs to interact with other applications or systems. For example, a program may need to automatically fill out forms on a website or interact with a game. By simulating mouse clicks and keyboard presses, developers can create virtual user interactions that mimic real user behavior. To simulate mouse clicks and keyboard presses in C using Linux, there are a few prerequisites. First, a basic understanding of the C programming language is necessary. Developers should be familiar with concepts such as variables, functions, and control structures. Additionally, knowledge of the Linux operating system and its APIs, application programming interfaces, is required. This includes understanding how to interact with the X window system, which is commonly used for graphical user interfaces in Linux. Setting up the development environment involves installing the necessary libraries and tools. The xlib library, which provides a low-level interface to the X window system, is commonly used for simulating mouse clicks and keyboard presses in C on Linux. Developers can install this library using package managers like apt or yum. Additionally, a text editor or an integrated development environment (IDE) can be used to write and compile the C code. In the upcoming sections of this book, we will explore in detail how to simulate mouse clicks and keyboard presses in C using Linux. We will cover topics such as understanding mouse events, simulating different types of mouse clicks, simulating keyboard events, handling mouse and keyboard events in both GUI and console applications, and advanced techniques for simulating mouse clicks and keyboard presses. By the end of this book, readers will have a comprehensive understanding of how to simulate mouse clicks and keyboard presses in C using Linux. They will be able to automate repetitive tasks, test user interfaces more efficiently, create virtual user interactions, and handle mouse and keyboard events in their own applications. Additionally, readers will gain insights into error handling, security considerations, performance optimization, and real-world applications of simulating mouse clicks and keyboard presses. 1.2 Benefits of simulating mouse clicks and keyboard presses. Simulating mouse clicks and keyboard presses in C using Linux can provide numerous benefits in various scenarios. Whether you are automating repetitive tasks, testing user interfaces, creating virtual user interactions, or enhancing accessibility for users with disabilities, the ability to simulate mouse clicks and keyboard presses can greatly simplify and streamline these processes. In this section, we will explore some of the key benefits of simulating mouse clicks and keyboard presses. 1. Increased efficiency and productivity. One of the primary benefits of simulating mouse clicks and keyboard presses is the ability to automate repetitive tasks. By writing a program to simulate these actions, you can save significant time and effort. Instead of manually performing the same actions over and over again, you can simply run your program and let it handle the task for you. This can greatly increase your efficiency and productivity, allowing you to focus on more important and complex tasks. 2. Accurate and consistent testing. Simulating mouse clicks and keyboard presses is also invaluable for testing user interfaces. By automating the testing process, you can ensure that the same actions are performed consistently and accurately every time. This eliminates the risk of human error and provides reliable results. Whether you are testing a web application, a game, or a GUI application, simulating user interactions can help you identify and fix any issues or bugs more efficiently. 3. Creating virtual user interactions. Simulating mouse clicks and keyboard presses can be used to create virtual user interactions in various scenarios. For example, if you are developing a virtual reality application or a simulation, you can use simulated mouse clicks and keyboard presses to mimic the actions of a user in the virtual environment. This can provide a more immersive and interactive experience for the users. 4. Enhancing accessibility. Simulating mouse clicks and keyboard presses can also play a crucial role in enhancing accessibility for users with disabilities. For individuals who have limited mobility or dexterity, performing certain actions using a physical mouse or keyboard can be challenging or even impossible. By simulating these actions, you can provide alternative methods for users to interact with applications and systems. This can greatly improve accessibility and inclusivity for a wider range of users. 5. Integration with other applications. Simulating mouse clicks and keyboard presses can be seamlessly integrated with other applications and tools. For example, you can use simulated interactions to automate tasks in web browsers, games, productivity tools, or even in automation scripts. This integration allows you to extend the functionality of existing applications and systems, making them more efficient and user-friendly. 6. Flexibility and customization. Simulating mouse clicks and keyboard presses in C using Linux provides a high level of flexibility and customization. Since you have full control over the code, you can tailor the simulated interactions to meet your specific requirements. You can define the exact sequence of mouse clicks and keyboard presses, specify the timing and duration of each action, and even simulate complex interactions such as mouse dragging or keyboard macros. This level of customization allows you to create powerful and sophisticated simulations. 7. Cross-platform compatibility. Another advantage of simulating mouse clicks and keyboard presses in C using Linux is the cross-platform compatibility. C is a widely supported programming language, and Linux is a popular operating system used by developers worldwide. By writing your simulation code in C and targeting Linux, you can ensure that your simulations can run on various platforms, including Windows, Mac OS, and other Unix-like systems. This cross-platform compatibility allows you to reach a wider audience and deploy your simulations on different environments. In conclusion, simulating mouse clicks and keyboard presses in C using Linux offers numerous benefits, including increased efficiency and productivity, accurate and consistent testing, the ability to create virtual user interactions, enhanced accessibility, seamless integration with other applications, flexibility and customization, and cross-platform compatibility. Whether you are automating tasks, testing user interfaces, creating virtual experiences, or improving accessibility, the ability to simulate user interactions can greatly simplify and enhance these processes. 1.3 Prerequisites for simulating mouse clicks and keyboard presses. Before diving into simulating mouse clicks and keyboard presses in C using Linux, there are a few prerequisites that you should be familiar with. These prerequisites will help you understand the concepts and techniques involved in simulating these events effectively. In this section, we will discuss the essential knowledge and tools you need to have before getting started. 1.3.1 C Programming Language. To simulate mouse clicks and keyboard presses in C, you should have a good understanding of the C programming language. Familiarity with C syntax, data types, control structures, functions, and pointers is crucial. You should be comfortable writing C code and have a basic understanding of how to compile and run C programs. 1.3.2 Linux Operating System. Simulating mouse clicks and keyboard presses in C requires a Linux operating system. Linux provides a powerful and flexible environment for developing and running C programs. It offers various libraries and tools that make it easier to interact with the system's input devices and simulate user events. 1.3.3 X Window System. The X window system, commonly referred to as X11 or X, is the standard windowing system used in Linux and other Unix-like operating systems. It provides the foundation for graphical user interfaces (GUIs) and allows applications to interact with the display, keyboard, and mouse. To simulate mouse clicks and keyboard presses, you need to understand how the X window system works and how to interact with it programmatically. This includes knowledge of X events, window management, and the xlib library, which provides a low-level interface to the X server. 1.3.4 xlib library. The xlib library is a C library that provides a low-level interface to the X window system. It allows you to create windows, handle events, and interact with the display, keyboard, and mouse. The xlib library provides functions for simulating mouse clicks and keyboard presses by generating appropriate X events. To simulate mouse clicks and keyboard presses in C, you need to be familiar with the xlib library and its functions for generating events. This includes understanding how to create an X display connection, create windows, handle events, and send synthetic events to the X server. 1.3.5 Development Environment. To develop and test your code for simulating mouse clicks and keyboard presses, you need a suitable development environment. This includes a text editor or integrated development environment (IDE) for writing your C code, a C compiler for compiling your code into executable binaries, and a terminal for running your programs. There are several popular text editors and IDEs available for Linux, such as Vim, Emacs, Sublime Text, and Visual Studio Code. You can choose the one that suits your preferences and workflow. As for the C compiler, GCC New Compiler Collection is a widely used and highly recommended compiler for C programming on Linux. 1.3.6 Basic Linux Command Line Skills. Having basic command line skills is essential for working with Linux and developing C programs. You should be comfortable navigating the file system, creating and editing files, compiling and running programs, and managing dependencies. Some basic command line skills that will be useful include navigating directories using CD, listing files and directories using ls, creating and editing files using Touch and Nano, compiling C programs using GCC, and running programs using /. 1.3.7 Familiarity with mouse and keyboard events. To effectively simulate mouse clicks and keyboard presses, you should have a good understanding of how these events work. This includes knowledge of different types of mouse clicks: left, right, middle keyboard key codes, modifiers, shift, control, alt and special keys, enter, escape, tab. Understanding the different types of mouse and keyboard events will help you simulate them accurately in your C programs. You should know how to generate the appropriate events based on the desired action, such as clicking a specific mouse button or pressing a particular key. 1.3.8 Problem Solving and Debugging Skills. Simulating mouse clicks and keyboard presses in C can be challenging at times, especially when dealing with complex interactions or troubleshooting issues. Therefore, having strong problem solving and debugging skills is crucial. You should be able to analyze problems, identify potential issues, and come up with effective solutions. Familiarity with debugging techniques, such as using print statements, debugging tools, and logging, will help you track down and fix any issues that may arise during development. By having a solid understanding of these prerequisites, you will be well prepared to start simulating mouse clicks and keyboard presses in C using Linux. In the next section, we will discuss how to set up your development environment to begin working on your simulations. 1.4 Setting up the development environment. Before we can start simulating mouse clicks and keyboard presses in C using Linux, we need to set up our development environment. This section will guide you through the necessary steps to ensure that you have all the tools and libraries required for this task. Installing the required packages. To begin, we need to install the necessary packages that will enable us to simulate mouse clicks and keyboard presses. The primary package we will be using is the X11 library, which provides a set of functions for interacting with the X window system, the default windowing system on Linux. To install the X11 library, open a terminal and run the following command. Sudo apt-get install lib11dev. This command will install the development files for the X11 library, allowing us to compile and link our code against it. Creating a new C project. Once the X11 library is installed, we can proceed to create a new C project. Open your favorite text editor or integrated development environment, IDE, and create a new file with a C extension. This file will serve as our main source code file, including the required headers. In our main source code file, we need to include the necessary headers to access the functions and data types provided by the X11 library. Add the following lines at the beginning of your source code file. Hashtag include less than saintio. H greater than hashtag include less than stdlib. H greater than hashtag include less than x11 xlib. H greater than. The saintio, H and stdlib. H headers are standard C headers that provide functions for input, output and memory management, respectively. The x11 xlib. H header is the main header file for the X11 library. Initializing the X11 display. Before we can simulate mouse clicks and keyboard presses, we need to initialize the X11 display. The display represents the physical screen and input devices connected to our system. Add the following code snippet after the header includes. Int main. Display equals x open display, null, if display equals null. Fprintf saintdir, unable to open the display. N, return 1. Rest of the code goes here. X close display, return 0. The xOpenDisplay function opens a connection to the X11 display. If the function returns null, it means that the display could not be opened, and we print an error message to the standard error stream using fprintf. We then return a non-zero value to indicate that an error occurred. Simulating mouse clicks and keyboard presses. With the X11 display initialized, we can now proceed to simulate mouse clicks and keyboard presses. The X11 library provides functions for generating and sending events to the X server, which in turn processes these events and performs the corresponding actions. To simulate a mouse click, we need to create an instance of the X event structure and set its type field to button press or button release, depending on whether we want to simulate a mouse button press or release. We also need to set the button field to the desired mouse button, e.g., button 1 for the left button, button 2 for the middle button, or button 3 for the right button. To simulate a keyboard press, we need to create an instance of the X event structure and set its type field to keypress. We also need to set the keycode field to the desired keycode, which can be obtained using the xKeySim to keycode function. Once we have set up the X event structure, we can use the xSendEvent function to send the event to the X server. The X server will then process the event and perform the corresponding action, such as generating a mouse click or simulating a keyboard press. Compiling and running the code. To compile the code, open a terminal and navigate to the directory where your source code file is located. Run the following command. gcco program_name source_code, CLX11. Replace program_name with the desired name for your executable file and source_code, C with the name of your source code file. Once the code is successfully compiled, you can run the program by executing the following command. Program_name. Make sure that you have the appropriate permissions to run the program. Conclusion. In this section, we have discussed the steps required to set up the development environment for simulating mouse clicks and keyboard presses in C using Linux. We installed the necessary packages, created a new C project, included the required headers, initialized the X11 display, and learned how to simulate mouse clicks and keyboard presses. We also covered the process of compiling and running the code. With the development environment set up, we can now proceed to explore the various techniques and functionalities for simulating mouse clicks and keyboard presses in C using Linux. 2. Simulating mouse clicks. 2.1 Understanding mouse events. In order to simulate mouse clicks in C using Linux, it is important to have a clear understanding of mouse events. Mouse events are actions performed by the user using the mouse, such as clicking, moving, or scrolling. These events are captured by the operating system and can be simulated programmatically. Mouse buttons. A typical mouse has 3 buttons: left, right, and middle. Each button generates a specific event when clicked. The left button is usually used for primary actions, such as selecting or dragging objects. The right button is commonly used for context menus or secondary actions. The middle button is often used for scrolling or opening links in a new tab. Mouse click events. Mouse click events occur when a mouse button is pressed and released. These events are essential for interacting with graphical user interfaces and controlling applications. When a mouse button is clicked, the operating system generates a specific event code that can be captured and simulated. Mouse movement events. Mouse movement events occur when the mouse is moved across the screen. These events provide information about the current position of the mouse cursor. Mouse movement events are crucial for simulating mouse clicks accurately, as they determine the target location for the simulated click. Mouse scroll events. Mouse scroll events occur when the user scrolls the mouse wheel up or down. These events are commonly used for scrolling through documents, web pages, or other scrollable content. Simulating mouse scroll events can be useful when automating tasks that involve scrolling. Mouse event codes. In Linux, mouse events are represented by event codes. These codes are specific to the input subsystem and can be accessed through the dev input event device file, where X represents the input device number. Each mouse event has a unique code that can be used to identify and simulate the desired action. Event handling. To simulate mouse clicks in C using Linux, it is necessary to handle mouse events programmatically. This involves capturing the desired mouse event, generating the corresponding event code, and sending it to the operating system. The operating system then interprets the event code and performs the simulated action. Event injection. Event injection is the process of programmatically generating and injecting mouse events into the system event queue. This allows the simulated events to be processed by the operating system as if they were generated by a physical mouse. Event injection can be achieved using system calls or libraries that provide low-level access to the input subsystem. Event synchronization. When simulating mouse clicks, it is important to synchronize the simulated events with the application or window being targeted. This ensures that the simulated click is performed at the correct location and time. Event synchronization can be achieved by waiting for specific conditions or using timing mechanisms to ensure accurate simulation. Limitations and considerations. Simulating mouse clicks in C using Linux has some limitations and considerations. Firstly, the ability to simulate mouse events may require elevated privileges or special permissions, depending on the operating system configuration. Additionally, the accuracy and reliability of simulated mouse clicks may vary depending on the application being targeted and the specific use case. Conclusion. Understanding mouse events is essential for simulating mouse clicks in C using Linux. Mouse click events, mouse movement events, and mouse scroll events are the key components of mouse interaction. By capturing and simulating these events programmatically, it is possible to automate tasks, test user interfaces, and enhance accessibility. However, it is important to consider the limitations and requirements of simulating mouse clicks to ensure accurate and reliable results. 2.2 Simulating left mouse clicks. Simulating left mouse clicks is a fundamental aspect of automating user interactions in a Linux environment. By simulating left mouse clicks, you can programmatically perform actions such as clicking buttons, selecting items, and triggering events in graphical user interfaces (GUIs) or console applications. In this section, we will explore how to simulate left mouse clicks using C in a Linux environment. Understanding left mouse click events. Before we dive into simulating left mouse clicks, it's essential to understand the underlying concept of mouse events. In a graphical user interface, a mouse click event occurs when a user presses and releases the left mouse button. This event is typically associated with a specific location on the screen, known as the mouse cursor's coordinates. To simulate a left mouse click, we need to replicate this event programmatically. Fortunately, Linux provides us with the necessary tools and libraries to achieve this. Simulating left mouse clicks with X11. In Linux, the X window system, X11, is the standard protocol for managing graphical user interfaces. X11 provides a set of functions and libraries that allow us to interact with the display server and simulate mouse events. To simulate a left mouse click using X11, we can utilize the XTest extension library. This library provides functions for generating synthetic input events, including mouse clicks. First, we need to include the necessary header files. Hashtag include less than X11 xlib. H greater than hashtag include less than X11 extensions xtest. h greater than next, we can create a function to simulate a left mouse click. Void simulate left click display int button. X-test fake button event display, button, true, current time, X-test fake button event display, button, false, current time, X flush display. In the simulate left click function, we use the X-test fake button event function to generate a button press event true and a button release event false for the specified button. The X flush function ensures that the events are sent to the display server immediately. To use this function, we need to open a connection to the display server and obtain a reference to the display. Display equals X open display null if display equals null. Fprintf saint unable to open display, n, exit 1. After simulating the left mouse click, we should close the display connection. X close display example, simulating left mouse clicks. Let's put everything together and create a simple example that simulates a left mouse click at a specific screen location. Hashtag include less than saintio, h greater than hashtag include less than stdlib, h greater than hashtag include less than x11 xlib. H greater than hashtag include less than x11 extensions xtest, h greater than. Void simulate left click display, int button, int x, int y. X-test fake motion event display, -1, x, y, current time x sync display, false. X-test fake button event display, button, true, current time x sync display, false. X-test fake button event display, button, false, current time x sync display, false. X flush display. Int main. Display equals X open display null if display equals null fprintf saint unable to open display, n, exit 1. Int screen width equals width of screen default screen of display int screen height equals height of screen default screen of display int clicks equals screen width 2. Int clicky equals screen height 2. Simulate left click display, button 1, clicks, clicky. X close display return 0. In this example, we simulate a left mouse click at the center of the screen. We calculate the screen dimensions using the width of screen and height of screen functions. The button 1 constant represents the left mouse button. Compile and run the program, and you should see a left mouse click being simulated at the specified screen location. Conclusion. Simulating left mouse clicks in C using Linux is made possible by the X11 protocol and the Xtest extension library. By understanding the concept of mouse events and utilizing the appropriate functions, we can programmatically simulate user interactions in graphical and console applications. In the next section, we will explore simulating right mouse clicks. 2.3 Simulating right mouse clicks. Simulating right mouse clicks can be useful in various scenarios, such as automating tasks, testing user interfaces, or creating virtual user interactions. In this section, we will explore how to simulate right mouse clicks using C on a Linux system. To simulate a right mouse click, we need to understand the underlying mechanism of mouse events. In Linux, mouse events are typically handled through the X window system, which provides an interface for interacting with the display server. The X window system uses a client-server architecture, where the client applications send requests to the server to perform various operations, including simulating mouse clicks. To simulate a right mouse click, we can use the Xtest extension library, which provides functions for generating synthetic input events. This library allows us to simulate mouse clicks, movements, and other mouse-related events. To use the Xtest extension library, we need to include the X11 extensions Xtest, header file and link against the XTST library. Here's an example code snippet that demonstrates how to simulate a right mouse click using the Xtest extension library. Hashtag include less than X11 extensions Xtest, h greater than. Void simulate right mouse click display, window, int button. Xtest fake button event display, button, true, current time, Xtest fake button event display, button, false, current time, X flush display. In the above code, the simulate right mouse click function takes 3 parameters, display, window, and button. The display parameter represents the connection to the X server, which can be obtained using the XOpenDisplay function. The window parameter specifies the target window on which the right mouse click should be simulated. The button parameter indicates the button number for the right mouse click event. Inside the simulate right mouse click function, we use the Xtest fake button event function to generate the synthetic button events. The first call to Xtest fake button event with the true parameter simulates the button press event, while the second call with the false parameter simulates the button release event. Finally, we call xflush to ensure that the generated events are sent to the X server. To use the simulate right mouse click function, we need to obtain the display connection and the target window. Here's an example code snippet that demonstrates how to simulate a right mouse click on the root window. Hashtag include less than x11 xlib. H greater than hashtag include less than x11 extensions xtest. H greater than. Int main. Display equals x open display null window root window equals default root window display. Simulate right mouse click display root window button 3. X close display return 0. In the above code, we first open the display connection using the xopenDisplay function. The null parameter specifies the default display. Then, we obtain the root window using the default root window macro. Finally, we call the simulate right mouse click function with the display, root window, and the button number for the right mouse click event, in this case, button 3. It's important to note that the button numbers may vary depending on the mouse configuration and the X server implementation. In the example above, we used button 3 to represent the right mouse button. You can refer to the X11 documentation or use tools like XEV to determine the button numbers for your specific setup. Simulating right mouse clicks can be combined with other mouse events, such as mouse movements or button combinations, to perform more complex interactions. By understanding the underlying mechanisms and utilizing the XTest extension library, you can create powerful simulations of user interactions in your C programs running on Linux. In the next section, we will explore how to simulate middle mouse clicks, which can be useful for certain applications and workflows. 2.4 Simulating middle mouse clicks. Simulating middle mouse clicks can be a useful feature in certain applications or scenarios. Middle mouse clicks are typically used for various purposes, such as opening links in new tabs, closing tabs, pasting clipboard content, and more. In this section, we will explore how to simulate middle mouse clicks using C on Linux. Understanding middle mouse clicks. Before we dive into simulating middle mouse clicks, let's first understand what a middle mouse click is. A middle mouse click is triggered when the user presses the scroll wheel button on their mouse. This button is usually located between the left and right mouse buttons. In Linux, middle mouse clicks are typically associated with the button number 2. This button number is used to identify the middle mouse click event when handling mouse events in C. Simulating middle mouse clicks in C. To simulate a middle mouse click in C on Linux, we can make use of the X11 library. The X11 library provides functions and structures for interacting with the X window system, which is the windowing system used in most Unix-like operating systems, including Linux. To simulate a middle mouse click, we need to perform the following steps. Open a connection to the X server using the xopenDisplay function. Create a fake mouse event using the XTest fake button event function. Set the necessary event properties, such as the button number, state, and window. Send the fake mouse event using the xSendEvent function. Close the connection to the X server using the xCloseDisplay function. Here's an example code snippet that demonstrates how to simulate a middle mouse click in C. Hashtag include less than x11 xlib. H greater than hashtag include less than x11 extensions xtest. H greater than. Void simulate middle mouse click. Display equals xopenDisplay null window root equals default root window display. Xtest fake button event display 2 true current time xtest fake button event display 2 false current time. Xflush display xCloseDisplay display. Int main. Simulate middle mouse click return 0. In the above code, we first open a connection to the X server using xopenDisplay null. We then obtain the root window using default root window display. Next, we simulate a middle mouse click by calling xtest fake button event twice. The first call simulates the button press event true and the second call simulates the button release event false. We pass the button number 2 as the first argument to xtest fake button event to indicate that we want to simulate a middle mouse click. After sending the fake mouse events, we flush the display using xFlushDisplay to ensure that the events are processed immediately. Finally, we close the connection to the X server using xCloseDisplay display. Testing the middle mouse click simulation. To test the middle mouse click simulation, you can compile and run the above code on a Linux system. Make sure you have the necessary X11 development libraries installed. After running the program, you should see that a middle mouse click is simulated. You can verify this by performing actions that are triggered by a middle mouse click, such as opening a link in a new tab or pasting clipboard content. Conclusion. Simulating middle mouse clicks in C on Linux can be achieved using the X11 library. By understanding the concepts and using the provided functions, you can incorporate middle mouse click simulations into your applications or scripts. Middle mouse click simulations can enhance user interactions and automate repetitive tasks, providing a more efficient and convenient user experience. 3. Simulating keyboard presses. 3.1 Understanding keyboard events. In order to simulate keyboard presses in C using Linux, it is important to have a clear understanding of keyboard events. Keyboard events refer to the actions performed by a user on a keyboard, such as pressing a key or releasing a key. These events are then translated into specific characters or actions by the operating system. Keyboard event types. There are several types of keyboard events that can be generated by a user. The most common types include key press. This event occurs when a key is physically pressed down on the keyboard. It is typically followed by a key release event. Key release. This event occurs when a key is released after being pressed down. It signifies the end of a key press event. Key repeat. Some keys on a keyboard have the ability to generate multiple key press events when held down for a certain period of time. This is known as key repeat. The operating system determines the repeat rate and generates the appropriate events. Modifier keys. Modifier keys, such as Shift, Control, and Alt, are special keys that modify the behavior of other keys when pressed in combination with them. These keys generate separate events and are often used to create key combinations. Keyboard event codes. Each key on a keyboard is assigned a unique code by the operating system. These codes are used to identify the specific key that was pressed or released. In Linux, keyboard event codes are defined in the Linux input event codes header file. The event codes are represented by integers and are divided into different categories, such as letters, numbers, function keys, and special keys. For example, the event code for the letter A is key_A, while the event code for the enter key is key_enter. Simulating keyboard events in C. To simulate keyboard events in C using Linux, you can make use of the U-input interface. The U-input interface allows you to create virtual input devices and generate keyboard events programmatically. Here are the basic steps to simulate keyboard events. Open the U-input device file for writing. This can be done using the open system call. Configure the virtual input device by setting the appropriate properties, such as the device name, supported event types, and event codes. This can be done using the ioctl system call. Generate keyboard events by writing event structures to the U-input device file. Each event structure contains information about the event type, event code, and event value. The event value can be set to 1 for key press events, 0 for key release events, or a specific value for key repeat events. Close the U-input device file when you are done simulating keyboard events. Example: simulating a key press. Let's take a look at a simple example that demonstrates how to simulate a key press event in C using Linux. Hashtag include less than saintio. H greater than hashtag include less than fcntl. H greater than hashtag include less than Linux U-input. H greater than. Int main. Int U-input underscore fd. Struct U-input underscore user underscore dev uadev. Struct input underscore event ev. Open the U-input device file for writing U-input underscore fd equals open dev U-input o underscore wrongly o underscore non-block if U-input underscore fd less than o. Pair failed to open U-input device, return 1. Configure the virtual input device ioctl U-input underscore fd, UI underscore set underscore evbit, EV underscore key ioctl U-input underscore fd, UI underscore set underscore key bit, key underscore a. Memset and uadev, 0, size of uadev sn printf, uadev.name. UINPUT underscore max underscore name underscore size, virtual keyboard, uadev.id, bus type equals bus underscore USB. uadev.id, vendor equals 0x1234, uadev.id, product equals 0x5678, uadev.id, version equals 1. Write U-input underscore FD, and uadev, size of uadev ioctl, U-input underscore FD, UI underscore dev underscore create. Simulate a key press event memset and EV, 0, size of EV, type equals EV underscore key, EV, code equals key underscore A, EV, value equals 1. Write U-input underscore FD, and EV, size of EV. Simulate a key release event memset and EV, 0, size of EV, type equals EV underscore key, EV, code equals key underscore A, EV, value equals 0. Write U-input underscore FD, and EV, size of EV. Destroy the virtual input device ioctl U-input underscore FD, UI underscore dev underscore destroy close U-input underscore FD. Return 0. In this example, we first open the U-input device file for writing. We then configure the virtual input device to support key events for the letter A. Next, we simulate a key press event by setting the event type to EV underscore key, the event code to key underscore A, and the event value to 1. Finally, we simulate a key release event by setting the event value to 0. This is just a basic example to get you started with simulating keyboard events in C using Linux. You can extend this code to simulate other key events, handle key combinations, or even simulate text input by generating a sequence of key press and release events. Understanding keyboard events is crucial for accurately simulating keyboard presses in your C programs. With this knowledge, you can create powerful applications that automate tasks, test user interfaces, or enhance accessibility for users with disabilities. 3.2 Simulating single key presses. Simulating single key presses is a fundamental aspect of automating user interactions with a computer system. In this section, we will explore how to simulate single key presses using C on a Linux platform. Simulating single key presses can be useful in various scenarios, such as automating repetitive tasks, testing user interfaces, and creating virtual user interactions. Understanding keyboard events. Before we dive into simulating single key presses, it is essential to understand how keyboard events work. When a key is pressed on a physical keyboard, it generates a keyboard event that is sent to the operating system. The operating system then processes the event and performs the appropriate action, such as displaying the corresponding character on the screen or triggering a specific function in an application. In order to simulate a single key press, we need to generate a keyboard event programmatically. This involves sending the appropriate signals to the operating system, mimicking the behavior of a physical key press. Simulating single key presses in C. To simulate single key presses in C on a Linux platform, we can make use of the X11 library. The X11 library provides functions and data structures for interacting with the X window system, which is the windowing system used by most Linux distributions. To begin, we need to include the necessary header files and initialize the X11 library. Here is an example code snippet that demonstrates how to simulate a single key press. Hashtag include less than X11 xlib. H greater than hashtag include less than X11 keysim. H greater than. Int main. Display equals X open display null window root equals default root window display. X test fake key event display, X keysim to key code display, XK underscore 8 true, 0 X flush display. Usleep 100,000. X test fake key event display, X keysim to key code display, XK underscore 8 false, 0 X flush display. X close display display. Return 0. In this example, we first open a connection to the X server using the X open display function. We then obtain the root window of the default screen using the default root window macro. Next, we use the xTestFakeKeyEvent function to simulate a key press. The first argument is the display connection, the second argument is the keycode corresponding to the desired key, in this case, the A key. The third argument indicates whether the key is being pressed or released, and the fourth argument is a set of modifier keys e.g., Shift, Control that are being held down during the key press. After simulating the key press, we flush the display using the xFlush function to ensure that the event is processed immediately. We then introduce a small delay using the uSleep function to allow time for the key press event to be recognized. Finally, we simulate the key release by calling xTestFakeKeyEvent again with the same keycode but with the third argument set to false. We flush the display once more and close the display connection using the xCloseDisplay function. Handling modifier keys. In addition to simulating single key presses, it is often necessary to simulate key combinations involving modifier keys such as Shift, Control, and Alt. Modifier keys modify the behavior of other keys when pressed simultaneously. To simulate key combinations, we can modify the fourth argument of the xTestFakeKeyEvent function to include the desired modifier keys. For example, to simulate pressing the A key while holding down the Shift key, we can use the following code. xTestFakeKeyEvent display, xkeysim to keycode display, xk underscore shift underscore L true, 0 xTestFakeKeyEvent display, xkeysim to keycode display, xk underscore 8 true, 0 X flush display. Usleep 100,000. xTestFakeKeyEvent display, xkeysim to keycode display, xk underscore 8 false, 0 xTestFakeKeyEvent display, xkeysim to keycode display, xk underscore shift underscore L false, 0 X flush display. In this example, we first simulate pressing the Shift key, followed by simulating the A key press. We then flush the display and introduce a delay. Finally, we simulate releasing the A key and the Shift key, and flush the display again. Conclusion. Simulating single key presses in C on a Linux platform allows us to automate user interactions and perform various tasks programmatically. By understanding keyboard events and utilizing the X11 library, we can simulate key presses and key combinations with ease. In the next section, we will explore simulating key combinations in more detail. 3.3 Simulating key combinations. Simulating key combinations is a powerful technique that allows you to simulate the pressing of multiple keys simultaneously or in a specific sequence. This can be useful in various scenarios, such as triggering keyboard shortcuts in applications or automating complex tasks that require specific key combinations. In C, simulating key combinations involves sending multiple key events in a specific order to the operating system. The operating system then interprets these events as if the keys were physically pressed on the keyboard. To achieve this, we can use the same techniques we discussed earlier for simulating single key presses. To simulate a key combination, we need to understand the concept of modifier keys. Modifier keys are special keys on the keyboard that modify the behavior of other keys when pressed in combination with them. Examples of modifier keys include Shift, Control, and Alt. By pressing a modifier key along with another key, we can trigger different actions or shortcuts. To simulate a key combination, we first need to simulate the press of the modifier keys and then simulate the press of the other keys in the desired order. We can achieve this by sending the appropriate key events to the operating system. Let's take an example of simulating the key combination, Ctrl+C, which is commonly used to interrupt or terminate a running program. In C, we can simulate this key combination using the following steps. Simulate the press of the Control key. Send a key press event for the Control key using the appropriate function or library in C. Simulate the press of the C key. Send a key press event for the C key using the appropriate function or library in C. Simulate the release of the C key. Send a key release event for the C key using the appropriate function or library in C. Simulate the release of the Control key. Send a key release event for the control key using the appropriate function or library in C. By following these steps, we can effectively simulate the key combination, Control plus C, in our C program running on Linux. It's important to note that the specific functions or libraries used for simulating key events may vary depending on the Linux distribution and the programming environment you are using. However, the general concept remains the same. Simulating key combinations can be extended to more complex scenarios where multiple modifier keys are involved or where a specific sequence of keys needs to be simulated. For example, simulating the key combination, Control plus Shift plus T, to open a new tab in a web browser, or simulating a series of keys to perform a specific action in a game. When simulating key combinations, it's crucial to consider the order in which the keys are pressed and released. The operating system interprets key events based on the order in which they are received. Therefore, if the order is incorrect, the desired action may not be triggered. In addition, it's important to handle any potential errors or exceptions that may occur during the simulation of key combinations. Proper error handling ensures that the program gracefully handles any unexpected situations and provides appropriate feedback to the user. Simulating key combinations in C using Linux opens up a wide range of possibilities for automating tasks, enhancing user interactions, and improving productivity. By understanding the concept of modifier keys and following the correct sequence of key events, you can effectively simulate complex key combinations in your C programs. 3.4 Simulating text input. Simulating text input is an essential aspect of automating tasks that involve entering text into applications or emulating user interactions. In this section, we will explore how to simulate text input using C on Linux. Understanding text input events. Text input events are different from keyboard press events. While keyboard press events simulate the pressing of individual keys, text input events simulate the input of complete strings or sentences. Simulating text input involves sending a sequence of keyboard press events that correspond to the characters in the desired text. Simulating single character input. To simulate single character input, we need to identify the corresponding key code for each character. In C, we can use the xk_* constants defined in the x11 keysim header file to represent the key codes. For example, xk_a represents the key code for the letter A. To simulate the input of a single character, we can use the xtestFakeKeyEvent function from the xtest library. This function takes the display, keycode, and various other parameters as arguments. We can use the xkeysim to keycode function to convert the key code to the corresponding keycode. Here's an example of simulating the input of the letter A. Hashtag include less than x11 xlib. H greater than hashtag include less than x11 keysim. H greater than hashtag include less than x11 extensions xtest. H greater than. Void simulate text char character. Display equals x open display null keycode equals x keysim to keycode display xk_a. Xtest fake key event display keycode true 0 xtest fake key event display keycode false 0. Xflush display xclose display. Int main. Simulate text A return 0. Simulating text strings. Simulating the input of complete text strings involves iterating over each character in the string and simulating the input of each character individually. We can use a loop to iterate over the characters and call the simulate text function for each character. Here's an example of simulating the input of the text string, hello, world. Hashtag include less than x11 xlib. H greater than hashtag include less than x11 keysim. H greater than hashtag include less than x11 extensions xtest. H greater than hashtag include less than string. H greater than. Void simulate text const char text. Display equals x open display null. For int I equals 0, I less than sterling text I plus keycode equals x keysim to keycode display text I. Xtest fake key event display keycode true 0 xtest fake key event display keycode false 0. Xflush display xclose display. Int main. Simulate text hello world return 0. Handling special characters and key combinations. Simulating text input may involve handling special characters and key combinations. Special characters such as newline, tab, and backspace can be simulated by using their respective key codes. Key combinations, such as Ctrl plus C or Ctrl plus V, can be simulated by sending multiple key press events in the correct order. To simulate special characters, we can use the xk_* constants for the respective characters. For example, xk_return represents the newline character. To simulate key combinations, we can use the xtestFakeKeyEvent function to simulate the press and release of each key in the combination. For example, to simulate Ctrl plus C, we would simulate the press and release of the Control key, followed by the press and release of the C key. Conclusion. Simulating text input in C on Linux allows us to automate tasks that involve entering text into applications or emulating user interactions. By understanding text input events, simulating single character input, simulating text strings, and handling special characters and key combinations, we can effectively automate text input in our applications. 4. Handling mouse and keyboard events. 4.1 Capturing mouse events. Capturing mouse events is an essential aspect of simulating mouse clicks and keyboard presses in C using Linux. By capturing mouse events, we can track the movement of the mouse, detect button clicks, and perform actions based on user interactions. In this section, we will explore how to capture mouse events in a Linux environment and use them to simulate mouse clicks. Understanding mouse events. Before we dive into capturing mouse events, let's first understand what mouse events are. Mouse events are generated when the user interacts with the mouse, such as moving the cursor or clicking the mouse buttons. These events provide information about the position of the mouse cursor, the type of button clicked, and any additional data associated with the event. In Linux, mouse events are typically handled through the input subsystem. The input subsystem provides a unified interface for handling various input devices, including mice. Mouse events are represented as input events and can be accessed through the dev input directory. Capturing mouse events. To capture mouse events in C using Linux, we need to open the appropriate input device file and read the events from it. The following steps outline the process of capturing mouse events. Open the input device file. The input device file for the mouse is usually located at dev input event, where X represents the event number assigned to the mouse. We can open this file using the open system call and obtain a file descriptor. Read mouse events. Once the input device file is opened, we can read mouse events from it using the read system call. The read function reads a specified number of bytes from the file descriptor into a buffer. Each mouse event is represented by a structure, such as struct input underscore event, which contains information about the event type, timestamp, and event data. Process mouse events. After reading the mouse events, we can process them based on their type. For example, if we are interested in capturing mouse button clicks, we can check the event type and handle the events accordingly. We can also extract additional information from the event structure, such as the button code or the position of the mouse cursor. Close the input device file. Once we have finished capturing mouse events, it is important to close the input device file using the close system call. This releases any system resources associated with the file descriptor. Example: capturing mouse button clicks. Let's consider an example where we want to capture mouse button clicks and print a message whenever a button is clicked. The following code snippet demonstrates how to capture mouse events and handle button clicks. Hashtag include less than Saintio. H greater than hashtag include less than FCNTL. H greater than hashtag include less than Linux input. H greater than. Int main. Int fd. Struct input underscore event ev. Open the input device file fd equals open dev input event o underscore rdonly if fd equals -1. Pair error opening input device, return 1. While 1 read mouse events read fd and ev size of struct input underscore event. Process mouse button clicks. If ev type equals ev underscore key in an ev code equals btn underscore left ev code equals btn underscore right ev code equals btn underscore middle if ev value equals 1. Printf mouse button clicked n. Close the input device file close fd. Return 0. In this example, we open the input device file dev input event replace x with the appropriate event number and continuously read mouse events using the read function. We check if the event type is ev underscore key indicating a button event and if the button code is btn underscore left, btn underscore right, or btn underscore middle representing the left, right, and middle mouse buttons, respectively. If the button is clicked ev value equals 1, we print a message indicating that a mouse button has been clicked. Conclusion. Capturing mouse events is a crucial step in simulating mouse clicks and keyboard presses in C using Linux. By understanding mouse events and using the input subsystem, we can track mouse movements, detect button clicks, and perform actions based on user interactions. In the next section, we will explore how to capture keyboard events and handle them in our applications. 4.2 Capturing keyboard events. Capturing keyboard events is an essential aspect of simulating keyboard presses in C using Linux. By capturing keyboard events, you can monitor and respond to user input, simulate key presses, and create interactive applications. In this section, we will explore how to capture keyboard events in a Linux environment using C. Understanding keyboard events. Before we dive into capturing keyboard events, it's important to understand how keyboard events are generated and processed by the operating system. When a key is pressed on the keyboard, it generates an electrical signal that is sent to the computer. The computer's keyboard controller then converts this signal into a scan code, which represents the specific key that was pressed. In Linux, keyboard events are handled by the kernel's input subsystem. The input subsystem receives the scan code from the keyboard controller and translates it into a keycode. The keycode represents the logical key that was pressed, such as A, Enter, or Shift. The input subsystem then generates an input event, which contains information about the keycode, the state of modifier keys e.g., Shift, Control, and the type of event e.g., key press, key release. Capturing keyboard events in C. To capture keyboard events in C on Linux, we can use the evdev interface provided by the kernel's input subsystem. The evdev interface allows us to read input events from input devices, including keyboards. Here's a step-by-step guide on how to capture keyboard events in C. Open the input device. To capture keyboard events, we need to open the input device corresponding to the keyboard. The input devices are typically located in the dev input directory and have names like event 0, event 1, etc. We can open the input device using the open system call and obtain a file descriptor. Read input events. Once the input device is opened, we can read input events from it using the read system call. The read system call reads a specified number of bytes from the input device into a buffer. Each input event has a fixed size, so we can read multiple events at once. Process input events. After reading input events, we need to process them to extract the relevant information. Each input event has a specific structure defined in the Linux input header file. We can cast the buffer containing the input events to the appropriate structure and access its fields to retrieve the keycode, modifier keys, and event type. Handle keyboard events. Once we have extracted the relevant information from the input events, we can handle them according to our application's requirements. For example, we can simulate key presses, respond to specific key combinations, or update the state of the application based on user input. Example: capturing keyboard events. Let's take a look at a simple example that demonstrates how to capture keyboard events in C using the evdev interface. Hashtag include less than saintio. H greater than hashtag include less than fcntl. H greater than hashtag include less than Linux input. H greater than. Int main. Int fd. Struct input underscore event ev. Open the input device fd equals open dev input event 0 inches, o underscore rdonly if fd equals -1. Pair error opening input device, return 1. Read and process input events while 1. Read fd and ev size of struct input underscore event. Check if it's a key press event if ev type equals ev underscore key and an ev value equals 1 printf key pressed %t(n) ev code. Close the input device close fd. Return 0. In this example, we open the input device dev input event 0 using the open system call. We then enter a loop where we continuously read input events using the read system call. If the event type is ev underscore key and the event value is 1 indicating a key press, we print the keycode using ev code. Conclusion. Capturing keyboard events is crucial for simulating keyboard presses and creating interactive applications in C using Linux. By understanding how keyboard events are generated and processed, and by utilizing the evdev interface, we can effectively capture and handle keyboard events in our C programs. In the next section, we will explore how to handle mouse and keyboard events in a GUI application. 4.3 Handling mouse and keyboard events in a GUI application. In a GUI graphical user interface application, handling mouse and keyboard events is essential for creating interactive and responsive user interfaces. By capturing and processing these events, you can enable users to interact with your application through mouse clicks and keyboard presses. In this section, we will explore how to handle mouse and keyboard events in a GUI application using C on Linux. Event-driven programming. GUI applications are typically event-driven, meaning they respond to user actions or events. These events can include mouse clicks, keyboard presses, mouse movement, and more. To handle these events, you need to set up event listeners or callbacks that are triggered when a specific event occurs. Handling mouse events. To handle mouse events in a GUI application, you need to capture the mouse events and perform the desired actions based on the event type. In C on Linux, you can use libraries like xlib or gtk+ to handle mouse events. Capturing mouse clicks. To capture mouse clicks, you can set up a mouse button press event listener. When a mouse button is pressed, the event listener will be triggered, and you can perform the necessary actions. For example, you can update the UI, execute a specific function, or navigate to a different screen. Here's an example of capturing a left mouse button click using xlib. Hashtag include less than x11 xlib h greater than. Void handle mouse click x event event. If event type equals button press in an event x button equals button 1 left mouse button clicked perform actions here. Int main display equals x open display null window root equals default root window display x event event. X select input display root button press mask. While 1 x next event display an event handle mouse click event. X close display return 0. Capturing mouse movement. In addition to mouse clicks, you may also want to capture mouse movement events. This can be useful for implementing features like dragging and dropping elements or tracking the mouse position. To capture mouse movement, you can set up a motion event listener. Here's an example of capturing mouse movement using xlib. Hashtag include less than x11 xlib h greater than. Void handle mouse movement x event event. If event type equals motion notify mouse moved perform actions here. Int main. Display equals x open display null window root equals default root window display x event. X select input display root pointer motion mask. While 1. X next event display an event handle mouse movement event. X close display return 0. Handling keyboard events. Similar to mouse events, handling keyboard events in a GUI application involves capturing keyboard presses and performing actions based on the pressed keys. Libraries like xlib or GTK+ can also be used to handle keyboard events in C on Linux. Capturing single key presses. To capture single key presses, you can set up a key press event listener. When a key is pressed, the event listener will be triggered, and you can perform the desired actions. For example, you can update the GUI, execute a specific function, or navigate through different elements. Here's an example of capturing a single key press using xlib. Hashtag include less than x11, xlib, h greater than. Void handle key press, x event. If event, type equals key pressed perform actions here. Int main. Display equals x open display null window root equals default root window display x event. X select input display, root, key press mask. While 1. X next event display, an event handle key press event. X close display return 0. Capturing key combinations. In addition to single key presses, you may want to capture key combinations, such as Ctrl+C or Shift+Enter. To capture key combinations, you can keep track of the state of modifier keys Ctrl, Shift, Alt and check for specific key combinations in the key press event listener. Here's an example of capturing a key combination using xlib. Hashtag include less than x11, xlib, h greater than. Void handle key press, x event. If event, type equals key press, check for key combination. If event, x key, state and control mask in an event, x key, keycode equals x key sim to keycode display, xk_c Ctrl+C pressed. Perform actions here. Int main. Display equals x open display null window root equals default root window display x event. X select input display, root, key press mask. While 1. X next event display, an event handle key press event. X close display return 0. Conclusion. Handling mouse and keyboard events in a GUI application is crucial for creating interactive and user-friendly interfaces. By capturing and processing these events, you can enable users to interact with your application effectively. In this section, we explored how to handle mouse and keyboard events using C on Linux, using libraries like xlib or GTK+. With this knowledge, you can now implement event-driven functionality in your GUI applications and provide a seamless user experience. 4.4 Handling mouse and keyboard events in a console application. In the previous sections, we discussed how to simulate mouse clicks and keyboard presses in various scenarios, such as GUI applications and web browsers. However, there may be situations where you need to handle mouse and keyboard events in a console application. In this section, we will explore how to achieve this using C on Linux. 4.4.1 Reading mouse events. To handle mouse events in a console application, we need to read input from the terminal and interpret it as mouse events. In Linux, the terminal provides a way to read mouse events by enabling the mouse reporting mode. This mode allows the terminal to send mouse events as escape sequences. To enable mouse reporting mode, we can use the ncurses library, which provides functions for terminal manipulation. The ncurses library allows us to set the terminal in mouse event mode and read the mouse events. Here's an example of how to enable mouse reporting mode and read mouse events in a console application. Hashtag include less than ncurses, h greater than. Int main. Init cr, cbreak, no echo, keypad, stdscr, true, mouse mask, all mouse events, null. Int ch, mevent event. While, ch equals getch, equals key f1, if ch equals key mouse, if get mouse, and event equals ok, if event. B state and button 1 clicked, handle left mouse button click, else if event. B state and button 3 clicked, handle right mouse button click. And when, return 0. In this example, we use the initcr function to initialize the ncurses library and set up the terminal for curses mode. The cbreak function disables line buffering, allowing us to read input character by character. The noecho function disables echoing of input characters to the screen. The keypad function enables the reading of function keys. Finally, the mouse mask function enables mouse event reporting for all mouse events. Inside the main loop, we use the getch function to read input from the terminal. If the input is a mouse event indicated by key_mouse, we use the getMouse function to retrieve the mouse event details. We can then check the bstate field of the mevent structure to determine which mouse button was clicked. 4.4.2 Reading keyboard events. In addition to handling mouse events, we may also need to handle keyboard events in a console application. Fortunately, the ncurses library provides functions for reading keyboard events as well. Here's an example of how to read keyboard events in a console application using the ncurses library. Hashtag include less than ncurses, h greater than. Int main. Init cr c break no echo keypad stdscr true. Int ch. While ch equals getch equals key underscore f1 handle keyboard events. And when return 0. In this example, we use the same setup code as before to initialize the ncurses library and set up the terminal for curses mode. Inside the main loop, we use the getch function to read input from the terminal. The getch function returns the ASCII value of the key that was pressed. We can then use conditional statements or a switch statement to handle different keyboard events based on their ASCII values. For example, we can check if the input is the ASCII value of the enter key and to handle the enter key press event. 4.4.3 Handling mouse and keyboard events together. In some cases, we may need to handle both mouse and keyboard events together in a console application. To achieve this, we can combine the code snippets from the previous sections. Here's an example of how to handle both mouse and keyboard events in a console application using the ncurses library. Hashtag include less than ncurses, h greater than. Int main. Init cr c break no echo keypad stdscr true mouse mask all underscore mouse underscore events null. Int ch mevent event. While ch equals getch equals key underscore f1 if ch equals key underscore mouse if get mouse and event equals okay if event. B state and button 1 underscore clicked handle left mouse button click else if event. B state and button 3 underscore clicked handle right mouse button click. Else. Handle keyboard events. And when return 0. In this example, we combine the code for reading mouse events and keyboard events into a single loop. If the input is a mouse event, we handle it accordingly. Otherwise, we treat it as a keyboard event and handle it separately. By combining the code for handling mouse and keyboard events, we can create console applications that respond to user input in a more interactive and dynamic manner. Conclusion. Handling mouse and keyboard events in a console application can be achieved using the ncurses library in C on Linux. By enabling mouse reporting mode and reading input from the terminal, we can capture mouse events and keyboard events and respond to them accordingly. This allows us to create console applications that provide a more interactive user experience. 5. Advanced techniques for simulating mouse clicks and keyboard presses. 5.1 Simulating mouse movement. Simulating mouse movement is an essential aspect of creating realistic user interactions in applications. By simulating mouse movement, you can accurately mimic the behavior of a user moving the mouse cursor across the screen. This can be useful in various scenarios, such as testing user interfaces, automating repetitive tasks, or creating virtual user interactions. In C, simulating mouse movement involves manipulating the mouse cursor's position on the screen. Linux provides several libraries and functions that allow you to achieve this. One such library is xlib, which provides a low-level interface to the X window system, the default windowing system on Linux. To simulate mouse movement using xlib, you need to perform the following steps. Open a connection to the X server using the xopenDisplay function. This function returns a pointer to the display structure, which represents the connection to the X server. Obtain the root window of the default screen using the default root window function. The root window is the top-level window that encompasses the entire screen. Use the xwarp pointer function to move the mouse cursor to the desired position on the screen. This function takes the display connection, source window, usually the root window, destination window, also usually the root window, and the X and Y coordinates of the destination position. Here's an example code snippet that demonstrates how to simulate mouse movement using xlib. Hashtag include less than x11, xlib, h greater than. Int main. Display equals xopenDisplay, null, window root equals default root window, display. Simulate mouse movement at 100, 100 xwarp pointer display, none, root, 0, 0, 0, 0, 100, 100. X close display, return 0. In the above code, we first open a connection to the X server using xopenDisplay, null. Then, we obtain the root window using default root window, display. Finally, we use xwarp pointer to move the mouse cursor to the position 100, 100 on the screen. It's important to note that simulating mouse movement using xlib requires the application to have the necessary permissions to access the X server. If the application is running with limited privileges, it may not be able to simulate mouse movement successfully. Additionally, simulating mouse movement alone may not be sufficient to create realistic user interactions. In most cases, you would also need to simulate mouse clicks or other mouse events in conjunction with mouse movement to accurately replicate user actions. Simulating mouse movement can be particularly useful in scenarios where you need to test the behavior of an application under different mouse cursor positions or when automating tasks that involve moving the mouse cursor to specific locations on the screen. In conclusion, simulating mouse movement in C using Linux involves manipulating the mouse cursor's position on the screen. By using libraries like xlib and functions like xwarp pointer, you can accurately simulate mouse movement to create realistic user interactions in your applications. Remember to consider the necessary permissions and other mouse events to achieve comprehensive simulation of user actions. 5.2 Simulating mouse dragging. Simulating mouse dragging is a powerful technique that allows you to simulate the movement of the mouse while holding down a button. This can be useful in various scenarios, such as dragging and dropping elements in a graphical user interface or emulating touch gestures on a touch-enabled device. To simulate mouse dragging in C using Linux, we need to understand the underlying concepts and functions involved. The basic idea is to generate a sequence of mouse events that mimic the movement of the mouse while a button is held down. Understanding mouse dragging. Mouse dragging involves three main events: mouse button press, mouse movement, and mouse button release. When a user clicks and holds a mouse button, the system registers a mouse button press event. As the user moves the mouse, the system generates a series of mouse movement events. Finally, when the user releases the mouse button, a mouse button release event is triggered. To simulate mouse dragging, we need to generate these events programmatically. This can be achieved by using the appropriate functions provided by the Linux input subsystem. Simulating mouse dragging in C. To simulate mouse dragging in C using Linux, we can utilize the U-input interface, which allows us to create virtual input devices and generate input events programmatically. Here are the steps to simulate mouse dragging. Open the U-input device for writing. Use the open function to open the dev U-input device file. Set the appropriate flags to enable writing. Enable the required input event types. Use the IOCTL function with the UI_set_evbit command to enable the required event types. Enable the EV_key event type for mouse button events. Enable the EV_rel event type for mouse movement events. Enable the required input event codes. Use the IOCTL function with the UI_set_keybit command to enable the required event codes. Enable the mouse button event codes btn_left, btn_right, btn_middle, etc. Enable the mouse movement event codes rel_x, rel_y, etc. Create the virtual input device. Use the IOCTL function with the UI_dev_create command to create the virtual input device. Set the appropriate properties for the device, such as the device name and capabilities. Generate the mouse dragging events. Use the write function to write the input events to the U-input device. Generate a mouse button press event by setting the appropriate event type, code, and value. Generate a series of mouse movement events by setting the relative X and Y coordinates. Generate a mouse button release event to indicate the end of the dragging operation. Destroy the virtual input device. Use the IOCTL function with the UI_dev_destroy command to destroy the virtual input device. By following these steps, you can simulate mouse dragging in your C program running on Linux. Remember to handle any errors that may occur during the process and clean up resources properly. Example: simulating mouse dragging. Here's a simplified example that demonstrates how to simulate mouse dragging in C using Linux. Hashtag include less than saintio. H greater than hashtag include less than fcntl. H greater than hashtag include less than unist. H greater than hashtag include less than Linux U input. H greater than int main. Int U input _fd equals open dev U input O_ronly O_non-block. Enable required event types IOCTL U input _fd UI_set_evbit EV_key IOCTL U input _fd UI_set_evbit EV_rel. Enable required event codes IOCTL U input _fd UI_set_keybit btn_left IOCTL U input _fd UI_set_keybit rel_x IOCTL U input _fd UI_set_keybit rel_y. Create virtual input device struct U input _user_dev UADEV IOCTL U input _fd UI_dev_create. Simulate mouse dragging struct input _event. Mouse button press event. Type equals EV_key event. Code equals btn_left event. Value equals 1. Write U input _fd an event. Size of event. Mouse movement event. Type equals EV_rel event. Code equals rel_x event. Value equals 10. Write U input _fd an event. Size of event. Event. Type equals EV_rel event. Code equals rel_y event. Value equals 10. Write U input _fd an event. Size of event. Mouse button release event. Type equals EV_key event. Code equals btn_left event. Value equals 0. Write U input _fd an event. Size of event. Destroy virtual input device IOCTL U input _fd UI_dev_destroy. Close U input _fd. Return 0. In this example, we open the dev U input device file, enable the required event types and codes, create a virtual input device, generate the mouse dragging events, and finally destroy the virtual input device. Remember to compile the program with the appropriate flags and run it with sufficient privileges to access the U input device. Conclusion. Simulating mouse dragging in C using Linux allows you to programmatically generate mouse movement events while holding down a button. This technique can be useful in various applications, such as GUI automation, game development, and accessibility enhancements. By understanding the underlying concepts and utilizing the Linux input subsystem, you can create powerful simulations of mouse dragging interactions. 5.3 Simulating mouse scrolling. Scrolling is a common action performed by users to navigate through content that extends beyond the visible area of a window or screen. In this section, we will explore how to simulate mouse scrolling using C on Linux. Understanding mouse scrolling. Mouse scrolling refers to the action of moving the scroll wheel on a mouse to scroll up or down within a window or document. The scroll wheel typically generates specific mouse events that can be captured and processed by applications to perform scrolling actions. In Linux, mouse scrolling events are usually handled by the X window system, which provides a mechanism for applications to receive and process these events. To simulate mouse scrolling, we need to generate the appropriate mouse events that correspond to scrolling actions. Simulating mouse scrolling in C. To simulate mouse scrolling in C on Linux, we can use the xtest extension library, which provides functions for generating X events. The xtest library allows us to simulate various mouse events, including scrolling. To simulate mouse scrolling, we need to perform the following steps. Open a connection to the X server using the xopenDisplay function. Create a new X event using the xtestFakeButton event function, specifying the button number corresponding to the scroll wheel. Set the event type to button press or button release, depending on whether we want to simulate scrolling up or down. Set the event detail to the button number corresponding to the scroll wheel. Generate the event using the xSendEvent function. Close the connection to the X server using the xCloseDisplay function. Here is an example code snippet that demonstrates how to simulate mouse scrolling in C. Hashtag include less than x11 xlib. H greater than hashtag include less than x11 extensions xtest. H greater than. Void simulate mouse scroll int button int direction. Display equals xopenDisplay null xtestFakeButton event display button true current time xtestFakeButton event display button false current time xFlush display. xCloseDisplay display. Int main. Simulate mouse scroll 4, 1, simulate scrolling up, simulate mouse scroll 5, 0, simulate scrolling down, return 0. In the above code, the simulate mouse scroll function takes two parameters, button and direction. The button parameter specifies the button number corresponding to the scroll wheel, usually button 4 for scrolling up and button 5 for scrolling down. The direction parameter indicates the scrolling direction, 1 for up and 0 for down. By calling the simulate mouse scroll function with the appropriate parameters, we can simulate mouse scrolling in our C program. Limitations and considerations. It's important to note that simulating mouse scrolling using the xtest library requires the X window system to be running. If the program is executed in a non-graphical environment or without an active X server, the scrolling simulation may not work as expected. Additionally, the behavior of mouse scrolling can vary across different applications and window managers. Some applications may handle scrolling events differently or may not respond to simulated scrolling events at all. Therefore, it's essential to test the scrolling simulation in the specific context where it will be used. Furthermore, simulating mouse scrolling is just one aspect of interacting with graphical user interfaces. Depending on the requirements of your application, you may need to combine mouse scrolling with other mouse or keyboard events to achieve the desired functionality. Conclusion. Simulating mouse scrolling in C on Linux can be achieved using the xtest extension library. By generating the appropriate mouse events, we can simulate scrolling up or down within a window or document. However, it's important to consider the limitations and variations in behavior across different applications and window managers when implementing mouse scrolling simulations. 5.4 Simulating keyboard macros. In addition to simulating individual key presses and combinations, another powerful technique for automating tasks and enhancing productivity is simulating keyboard macros. A keyboard macro is a sequence of keyboard inputs that can be recorded and replayed with a single command. This allows you to automate repetitive tasks that involve a series of keystrokes, such as filling out forms, executing complex commands, or performing text transformations. Understanding keyboard macros. A keyboard macro typically consists of a series of key presses, delays, and special commands. When recording a macro, the system captures the sequence of keys you press and the timing between them. This recorded sequence can then be replayed later, either in real time or at an accelerated speed. Keyboard macros can be particularly useful when performing repetitive tasks that involve a fixed sequence of keystrokes. For example, if you frequently need to enter your email address in various forms, you can record a macro that types out your email address and then assign it to a shortcut key. Whenever you need to enter your email address, you can simply press the shortcut key, and the macro will automatically type it for you. Recording keyboard macros. To record a keyboard macro in C using Linux, you can utilize the X11 library, which provides functions for simulating keyboard events. The X11 library allows you to capture key press and release events, as well as modify the state of modifier keys such as Shift, Control, and Alt. To start recording a macro, you need to create a loop that continuously checks for keyboard events. Within this loop, you can capture each key press and release event and store them in a data structure or file. You can also record the timing between key events using the system clock or a timer function. During the recording process, you may want to include additional logic to handle special commands or pauses. For example, you can add a command to pause the macro recording when a specific key combination is pressed, or to insert a delay between key events. Replaying keyboard macros. Once you have recorded a keyboard macro, you can replay it by simulating the recorded key events. To do this, you need to iterate through the recorded events and use the X11 library functions to simulate each key press and release event. When replaying a macro, you can choose to execute the events in real time or at an accelerated speed. For real-time execution, you can simply use a loop with a delay between each event to mimic the original timing. Alternatively, you can modify the timing between events to speed up the execution, allowing the macro to complete faster. During the replay process, you may also want to include additional logic to handle errors or interruptions. For example, you can check if a specific window or application is active before executing the macro, or add error handling code to handle cases where a key event fails to simulate. Advanced techniques for keyboard macros. Keyboard macros can be enhanced with additional features to make them more versatile and powerful. Here are a few advanced techniques you can consider. Parameterization. Allow the user to input dynamic values during macro execution. For example, you can prompt the user to enter a file name or a search term and use that input within the macro. Conditional logic. Include conditional statements within the macro to perform different actions based on specific conditions. This can be useful for creating macros that adapt to different scenarios or handle exceptions. Loops. Implement looping structures within the macro to repeat a sequence of key events multiple times. This can be helpful for automating tasks that require repetitive actions, such as filling out multiple forms or performing batch operations. Error handling. Add error handling code to gracefully handle unexpected situations or errors during macro execution. This can include displaying error messages, logging errors, or providing options for the user to retry or skip certain steps. By incorporating these advanced techniques, you can create more flexible and robust keyboard macros that can handle a wider range of tasks and scenarios. Conclusion. Simulating keyboard macros in C using Linux provides a powerful tool for automating repetitive tasks and enhancing productivity. By recording and replaying sequences of key events, you can automate complex actions, streamline workflows, and save valuable time. With the ability to add advanced features such as parameterization, conditional logic, loops, and error handling, keyboard macros can become even more versatile and adaptable to various scenarios. Experiment with keyboard macros in your C programs and discover the immense potential they offer for automating tasks and improving efficiency. 6. Error handling and troubleshooting. 6.1 Common errors and issues. Simulating mouse clicks and keyboard presses in C using Linux can be a complex task, and it is not uncommon to encounter errors and issues during the development process. In this section, we will discuss some of the common errors and issues that you may come across and provide possible solutions to help you troubleshoot and resolve them. 1. Incorrect event handling. One common error when simulating mouse clicks and keyboard presses is incorrect event handling. This can occur when the events are not properly captured or processed by the application. It can result in unexpected behavior or the simulation not working at all. To resolve this issue, ensure that you are correctly capturing and handling the events in your code. Double-check that you are using the appropriate event types and that you are properly registering the event handlers. Additionally, make sure that you are correctly mapping the events to the desired actions, such as mouse clicks or keyboard presses. 2. Timing issues. Timing issues can also arise when simulating mouse clicks and keyboard presses. These issues occur when the timing of the simulated events is not synchronized with the application or system's expected timing. This can lead to events being missed or executed at the wrong time. To address timing issues, it is crucial to ensure that the simulated events are timed correctly. Consider using timers or delays to synchronize the events with the application's expected timing. Additionally, make sure that you are not overwhelming the system with too many events at once, as this can also cause timing problems. 3. Compatibility issues. Compatibility issues can occur when the code for simulating mouse clicks and keyboard presses is not compatible with the specific Linux distribution or version you are using. This can result in compilation errors or runtime issues. To resolve compatibility issues, ensure that you are using the appropriate libraries and APIs for your Linux distribution and version. Double-check the documentation and make any necessary adjustments to your code to ensure compatibility. Additionally, consider testing your code on different Linux distributions or versions to ensure broader compatibility. 4. Insufficient privileges. Simulating mouse clicks and keyboard presses often requires elevated privileges, especially when interacting with system-level processes or applications. If your code does not have sufficient privileges, it may encounter errors or fail to execute the simulated events. To address this issue, ensure that your code is running with the necessary privileges. This may involve running the code as a superuser or using tools like sudo to elevate the privileges temporarily. However, exercise caution when granting elevated privileges to your code, as it can pose security risks if not handled properly. 5. Lack of error handling. Another common issue is the lack of proper error handling in the code. Without adequate error handling, it can be challenging to identify and resolve issues when they occur. This can lead to unexpected behavior or the inability to diagnose the cause of the problem. To mitigate this issue, implement robust error handling mechanisms in your code. Use error codes or exceptions to capture and handle errors effectively. Additionally, consider logging error messages or generating error reports to aid in troubleshooting and debugging. 6. Interference from other applications. Interference from other applications running on the system can also cause errors and issues when simulating mouse clicks and keyboard presses. This can occur when other applications are capturing or intercepting the events, resulting in conflicts or unexpected behavior. To minimize interference from other applications, consider running your code in isolation or ensuring that conflicting applications are not active while running your simulation. Additionally, you can explore techniques such as disabling event capturing by other applications or using low-level event handling to bypass interference. 7. Hardware limitations. Hardware limitations can also impact the simulation of mouse clicks and keyboard presses. Certain hardware configurations or devices may not be fully compatible with the code or may have limitations that prevent accurate simulation. To address hardware limitations, ensure that your code is compatible with the specific hardware configurations you are using. Consider testing your code on different hardware setups to identify any limitations or compatibility issues. Additionally, consult the documentation or resources specific to your hardware to understand any constraints or workarounds that may be required. In conclusion, simulating mouse clicks and keyboard presses in C using Linux can encounter various errors and issues. By understanding and addressing these common problems, you can enhance the reliability and effectiveness of your simulations. Remember to thoroughly test your code, implement proper error handling, and ensure compatibility with your Linux distribution and hardware setup. 6.2 Debugging Techniques. Debugging is an essential part of software development, including when working with simulations of mouse clicks and keyboard presses in C using Linux. Debugging techniques help identify and fix errors, ensuring that the simulated interactions work as intended. In this section, we will explore some common debugging techniques that can be applied to troubleshoot issues in your code. 6.2.1 Debugging Tools. Linux provides a range of powerful debugging tools that can assist in identifying and resolving issues in your code. Some commonly used tools include 1. GDB New Debugger. GDB is a command line debugger that allows you to analyze and debug your C code. It provides features like breakpoints, stepping through code, examining variables, and more. By running your program with GDB, you can track down the source of errors and understand the flow of execution. 2. Valgrind. Valgrind is a dynamic analysis tool that helps detect memory leaks, memory errors, and other memory-related issues. By running your program through Valgrind, you can identify memory-related bugs that may cause unexpected behavior or crashes. 3. Strace. Strace is a system call tracer that allows you to monitor the system calls made by your program. It can be useful for understanding how your program interacts with the operating system and identifying any issues related to system calls. 4. ltrace. ltrace is a library call tracer that helps you track the library calls made by your program. It can be particularly useful when working with external libraries or APIs, as it allows you to see the function calls and their arguments. 6.2.2 Debugging Techniques. When debugging your code, it's important to have a systematic approach to identify and fix issues. Here are some techniques that can help you in the process. 1. Reproduce the issue. Start by reproducing the issue consistently. Identify the specific scenario or input that triggers the problem. Having a reliable way to reproduce the issue will make it easier to debug and validate any fixes. 2. Use debugging statements. Inserting debugging statements in your code can provide valuable insights into the program's execution flow. Print statements or log messages can help you track the values of variables, identify the point of failure, and understand the program's behavior. 3. Breakpoints. Set breakpoints in your code using a debugger like GDB. Breakpoints allow you to pause the execution of your program at specific points, giving you the opportunity to examine the state of variables and step through the code line by line. 4. Step through the code. Use the step-by-step execution feature of the debugger to analyze the flow of your program. Stepping through the code allows you to observe how variables change, identify any unexpected behavior, and pinpoint the location of errors. 5. Inspect variables. While debugging, it's crucial to inspect the values of variables at different points in your code. This can help you identify incorrect values, uninitialized variables, or unexpected changes that may be causing the issue. 6. Analyze error messages. Pay close attention to error messages and warnings generated by the compiler or runtime environment. Error messages often provide valuable information about the nature of the problem and can guide you towards the solution. 7. Divide and conquer. If you're dealing with a complex issue, consider dividing your code into smaller sections and testing each section independently. This approach can help narrow down the source of the problem and make it easier to isolate and fix the issue. 8. Use debugging tools. Leverage the power of debugging tools like GDB, Valgrind, Strace, and ltrace to gain deeper insights into your code's behavior. These tools can help you identify memory leaks, track system and library calls, and analyze the execution flow. 6.2.3 Best Practices for Debugging. To make your debugging process more effective, consider following these best practices. 1. Start with simple cases. When encountering an issue, start by testing the simplest possible case that reproduces the problem. This approach can help you identify whether the issue is specific to a particular scenario or a more general problem. 2. Keep a record. Maintain a record of the steps you've taken during the debugging process. This can include the changes you've made, the results you've observed, and any insights gained. Having a record can help you track your progress and avoid repeating unsuccessful attempts. 3. Collaborate and seek help. Don't hesitate to seek help from colleagues, online communities, or forums when you're stuck. Collaborating with others can provide fresh perspectives and insights that may lead to a solution. 4. Test and validate fixes. After making changes to your code, thoroughly test and validate the fixes. Ensure that the issue is resolved and that the changes do not introduce new bugs or unexpected behavior. 5. Document the solution. Once you've successfully resolved an issue, document the solution for future reference. This documentation can serve as a valuable resource for yourself and others who may encounter similar problems in the future. Debugging is an iterative process that requires patience and attention to detail. By applying the techniques and best practices outlined in this section, you can effectively identify and resolve issues in your code, ensuring that your simulations of mouse clicks and keyboard presses work as intended. 6.3 Logging and error reporting. When developing applications that simulate mouse clicks and keyboard presses in C using Linux, it is essential to implement robust logging and error reporting mechanisms. These features help in identifying and resolving issues during the development and deployment stages. In this section, we will explore the importance of logging and error reporting and discuss some best practices to implement them effectively. 6.3.1 Importance of logging. Logging plays a crucial role in understanding the behavior of an application and diagnosing problems. It allows developers to track the execution flow, monitor the application's performance, and identify potential issues. When simulating mouse clicks and keyboard presses, logging can provide valuable insights into the simulated events, their timing, and any errors encountered during the process. By logging relevant information, such as the type of event being simulated, the target window or application, and the result of the simulation, developers can gain a better understanding of the application's behavior. This information can be used for debugging purposes, performance optimization, and auditing simulated interactions. 6.3.2 Implementing logging. To implement logging in a C application, developers can use various techniques. One common approach is to write log messages to a file. This can be achieved by opening a file in append mode and writing log messages to it using functions like fprintf or fwrite. It is important to include relevant information in the log messages, such as timestamps, event details, and any relevant error codes or messages. Another approach is to use a logging library or framework that provides more advanced features, such as log levels, log rotation, and log filtering. Popular logging libraries for C include log4c, syslog, and spdlog. These libraries offer a wide range of functionalities and can simplify the process of implementing logging in an application. When simulating mouse clicks and keyboard presses, it is recommended to log not only successful simulations but also any errors or exceptions encountered. This helps in identifying and resolving issues promptly. Additionally, logging the input parameters and output results of the simulation can aid in troubleshooting and reproducing specific scenarios. 6.3.3 Error reporting. In addition to logging, error reporting is crucial for providing feedback to users and developers when something goes wrong during the simulation process. Error reporting allows users to understand why a simulation failed and provides developers with valuable information to diagnose and fix the underlying issue. When an error occurs, it is important to provide clear and concise error messages that describe the problem and suggest possible solutions. The error messages should be informative and avoid technical jargon whenever possible. Including relevant details, such as the type of event being simulated, the target application or window, and any error codes or messages received from the operating system, can greatly assist in troubleshooting. In C, error reporting can be implemented using error codes or error structures. Error codes can be defined as constants or enumerated types, representing different types of errors that can occur during the simulation process. When an error occurs, the appropriate error code can be returned from the function responsible for the simulation. Developers can then use these error codes to generate meaningful error messages for the user or log them for further analysis. Alternatively, error structures can be used to encapsulate detailed information about the error, such as the error code, error message, and additional context-specific data. This approach allows for more flexibility in handling and reporting errors, as it provides a structured way to convey relevant information. 6.3.4 Best Practices for Logging and Error Reporting. To ensure effective logging and error reporting in applications that simulate mouse clicks and keyboard presses, consider the following best practices. Use meaningful log messages. Log messages should provide enough information to understand the context and purpose of the log entry. Include relevant details such as timestamps, event types, and any relevant error codes or messages. Log both successful and failed simulations. Logging successful simulations helps in tracking the application's behavior and performance. Logging failed simulations provides valuable information for troubleshooting and resolving issues. Implement log levels. Use different log levels, e.g., debug, info, warning, error, to categorize log messages based on their importance. This allows developers to filter log messages based on their needs and focus on the most critical information. Consider log rotation. If the log file grows too large, implement log rotation to manage disk space efficiently. Log rotation involves creating new log files periodically or based on size limits and archiving or deleting older log files. Provide clear and concise error messages. Error messages should be user-friendly and provide enough information to understand the problem. Avoid technical jargon and provide suggestions for resolving the issue whenever possible. Handle errors gracefully. When an error occurs, handle it gracefully by cleaning up any resources and providing appropriate feedback to the user. This helps in maintaining a good user experience and prevents unexpected application behavior. By following these best practices, developers can ensure that logging and error reporting are effective in identifying and resolving issues during the development and deployment stages of applications that simulate mouse clicks and keyboard presses in C using Linux. In the next section, we will discuss some troubleshooting tips and tricks that can help in resolving common issues encountered during the simulation process. 6.4 Troubleshooting Tips and Tricks. Simulating mouse clicks and keyboard presses in C using Linux can sometimes be a complex task, and it's not uncommon to encounter issues or errors along the way. In this section, we will discuss some troubleshooting tips and tricks to help you overcome common problems and ensure smooth execution of your simulated interactions. 1. Verify dependencies and libraries. Before diving into troubleshooting, it's essential to ensure that you have all the necessary dependencies and libraries installed on your Linux system. Check if you have the required development packages, such as xlib or xtest, installed. These libraries provide the necessary functions and structures for simulating mouse clicks and keyboard presses. If you encounter errors related to missing libraries or undefined functions, make sure to install the appropriate packages using your package manager. For example, on Ubuntu, you can use the apt command to install missing libraries. Sudo apt install lib11 dev libots dev2. Check permissions and access. When simulating mouse clicks and keyboard presses, it's crucial to have the necessary permissions and access rights. If you are running your program as a regular user, make sure that you have the required permissions to access the input devices. In some cases, you might need to run your program with elevated privileges. Try running your code with sudo to see if the issue persists. However, be cautious when running programs with elevated privileges, as it can have security implications. 3. Debugging techniques. When troubleshooting, it's essential to have effective debugging techniques in place. Utilize debugging tools like GDB to step through your code and identify any logical or runtime errors. Set breakpoints at critical points in your code to inspect variables and track the flow of execution. Additionally, consider using logging statements to output relevant information during runtime. This can help you trace the execution path and identify any unexpected behavior or errors. Logging can be especially useful when dealing with complex simulations involving multiple mouse clicks or keyboard presses. 4. Error handling and exception handling. Implementing proper error handling and exception handling mechanisms in your code can greatly aid in troubleshooting. When simulating mouse clicks and keyboard presses, it's crucial to handle any potential errors gracefully. Use error codes or exceptions to indicate and handle errors during the simulation process. This will allow you to catch and address any issues that arise, providing more informative error messages to aid in troubleshooting. 5. Test in different environments. Sometimes, issues may arise due to specific configurations or setups. To ensure the reliability and compatibility of your simulated interactions, test your code in different environments and setups. Try running your code on different Linux distributions, desktop environments, or even virtual machines. This can help you identify any platform-specific issues and ensure that your code works as expected across various setups. 6. Community support and forums. If you encounter persistent issues or errors that you can't resolve on your own, don't hesitate to seek help from the community. Online forums, developer communities, and dedicated programming communities can be valuable resources for troubleshooting. Post your questions or issues on relevant forums or discussion boards, providing detailed information about the problem you're facing. Often, experienced developers or community members can provide insights, suggestions, or even solutions to help you overcome the obstacles you're facing. 7. Documentation and examples. When troubleshooting, always refer to the official documentation and examples provided by the libraries or frameworks you are using. The documentation often contains valuable information about common issues, troubleshooting steps, and best practices. Additionally, explore existing examples or sample code that demonstrates simulating mouse clicks and keyboard presses in C using Linux. Analyzing and understanding these examples can provide insights into potential pitfalls and how to avoid them. 8. Incremental development and testing. To minimize troubleshooting efforts, adopt an incremental development and testing approach. Instead of writing a large chunk of code and then testing it all at once, break down your implementation into smaller, manageable parts. After implementing each part, test it thoroughly to ensure it functions as expected. This approach allows you to identify and address issues early on, making troubleshooting more manageable and efficient. 9. Stay updated. Keep your development environment, libraries, and dependencies up to date. Regularly check for updates and security patches for the libraries you are using. Newer versions often include bug fixes and improvements that can help resolve known issues. Additionally, stay updated with the latest developments and advancements in simulating mouse clicks and keyboard presses. Follow relevant blogs, forums, or newsletters to stay informed about any new techniques, tools, or best practices that can enhance your simulations. By following these troubleshooting tips and tricks, you can overcome common issues and ensure the smooth execution of your simulated mouse clicks and keyboard presses in C using Linux. Remember to approach troubleshooting systematically, utilizing debugging techniques, documentation, and community support to resolve any obstacles you encounter. 7. Integration with other applications. 7.1 Simulating mouse clicks and keyboard presses in web browsers. Simulating mouse clicks and keyboard presses in web browsers can be a powerful tool for automating tasks, testing web applications, and enhancing user experience. In this section, we will explore how to simulate mouse clicks and keyboard presses in web browsers using C on Linux. Simulating mouse clicks. Simulating mouse clicks in web browsers involves emulating the behavior of a physical mouse click event. This can be useful for automating tasks such as clicking buttons, selecting checkboxes, or triggering JavaScript events on web pages. To simulate a mouse click in a web browser, we need to interact with the browser's document object model (DOM) using a library like libedo or XDO tool. These libraries provide functions to move the mouse cursor, click at specific coordinates, and perform other mouse-related actions. Here's an example of simulating a mouse click using libedo. Hashtag include less than XDO, H greater than. Int main. XDO underscore T asterisk XDO equals XDO underscore new, null, XDO underscore move underscore mouse, XDO, 500, 0, XDO underscore click underscore window, XDO, CURRENTWINDOW, 1, XDO underscore free, XDO. Return 0. In this example, we create a new XDO underscore T object using XDO underscore new, and move the mouse cursor to the coordinates 500, using XDO underscore move underscore mouse. Then, we simulate a left mouse click on the current window using XDO underscore click underscore window. Simulating keyboard presses. Simulating keyboard presses in web browsers allows us to automate text input, trigger keyboard shortcuts, or interact with form fields on web pages. Similar to simulating mouse clicks, simulating keyboard presses in web browsers requires interacting with the browser's DOM. We can use libraries like libedo or XDO tool to send keyboard events to the browser. Here's an example of simulating a keyboard press using libedo. Hashtag include less than XDO, H greater than. Int main. XDO underscore T asterisk XDO equals XDO underscore new, null. XDO underscore enter underscore text underscore window, XDO, CURRENTWINDOW, hello, world, 100,000, XDO underscore free, XDO. Return 0. In this example, we create a new XDO underscore T object using XDO underscore new, and simulate typing the text, hello, world, into the current window using XDO underscore enter underscore text underscore window. The last parameter specifies the delay between each key press in microseconds. Interacting with web browsers. To simulate mouse clicks and keyboard presses in web browsers, we need to identify the target browser window or tab. This can be done by using the window title, process ID, or other window identification methods. Once we have identified the target browser window, we can use the appropriate functions from libedo or XDO tool to simulate the desired mouse clicks or keyboard presses. It's important to note that simulating user interactions in web browsers may have limitations or security restrictions. Some web browsers may have built-in security measures to prevent automated interactions, such as CAPTCHAs or JavaScript-based protections. Additionally, simulating interactions in web browsers may not work consistently across different browser versions or configurations. Considerations and best practices. When simulating mouse clicks and keyboard presses in web browsers, it's important to consider the following best practices. Target specific elements. Instead of relying on mouse coordinates, try to target specific elements on the web page using their unique identifiers or CSS selectors. This ensures more reliable and maintainable simulations. Handle delays. Some web applications may have animations or asynchronous behavior that requires waiting for certain events to complete before simulating the next action. Use appropriate delays or wait for specific DOM events to ensure accurate simulations. Test across different browsers. Test your simulations across different web browsers to ensure compatibility and consistent behavior. Different browsers may have different DOM structures or event handling mechanisms. Handle errors gracefully. When simulating interactions in web browsers, errors can occur due to various reasons such as network issues or changes in the web page structure. Implement error handling mechanisms to gracefully handle such situations and provide meaningful feedback to the user. By following these best practices, you can effectively simulate mouse clicks and keyboard presses in web browsers using C on Linux, enabling automation, testing, and enhanced user experiences. 7.2 Simulating mouse clicks and keyboard presses in games. Simulating mouse clicks and keyboard presses in games can be a powerful tool for enhancing the gaming experience and automating certain tasks. Whether you want to automate repetitive actions, create macros, or simulate complex sequences of inputs, understanding how to simulate mouse clicks and keyboard presses in games can give you a competitive edge and make your gaming sessions more efficient. Simulating mouse clicks in games. Simulating mouse clicks in games involves emulating the actions of a physical mouse, such as left click, right click, and middle click. These actions can be used to interact with in-game objects, navigate menus, or perform specific actions. To simulate mouse clicks in games using C on Linux, you can utilize libraries like X11 or STL, Simple Direct Media Layer. These libraries provide functions and structures that allow you to simulate mouse events programmatically. The basic steps to simulate a mouse click in a game are as follows. Initialize the library and create a window or surface to capture mouse events. Set the position of the mouse cursor to the desired location on the screen. Generate a mouse event, such as a left click, right click, or middle click, at the specified position. Handle any additional actions or events triggered by the simulated mouse click. By combining these steps, you can create complex sequences of mouse clicks to automate tasks or perform specific actions in games. Simulating keyboard presses in games. Simulating keyboard presses in games allows you to automate actions that would typically require manual input. This can be useful for executing complex combinations of keys, creating macros, or automating repetitive tasks. To simulate keyboard presses in games using C on Linux, you can again utilize libraries like X11 or STL. These libraries provide functions and structures that allow you to simulate keyboard events programmatically. The process of simulating keyboard presses in games involves the following steps. Initialize the library and create a window or surface to capture keyboard events. Generate a keyboard event by specifying the key code or character to be pressed. Handle any additional actions or events triggered by the simulated keyboard press. By combining these steps, you can create powerful automation scripts or macros that can execute complex sequences of keyboard inputs in games. Considerations for simulating mouse clicks and keyboard presses in games. When simulating mouse clicks and keyboard presses in games, there are a few considerations to keep in mind. Game compatibility. Not all games may support or allow the simulation of mouse clicks and keyboard presses. Some games may have built-in anti-cheat mechanisms or restrictions that prevent the use of simulated inputs. It's important to check the game's terms of service or consult the game's community to ensure that simulating inputs is allowed. Timing and synchronization. Timing is crucial when simulating inputs in games. Some games may have strict timing requirements for certain actions, and simulating inputs too quickly or too slowly may result in unintended consequences or inaccuracies. It's important to understand the game's mechanics and timing requirements to ensure accurate simulation. Game detection. Some games may have mechanisms in place to detect simulated inputs and prevent cheating. These mechanisms can range from simple detection of repeated patterns to more advanced detection algorithms. It's important to be aware of these mechanisms and take steps to avoid detection if necessary. User experience. Simulating inputs in games should enhance the user experience and not disrupt the gameplay or fairness of the game. It's important to use simulated inputs responsibly and ethically, ensuring that they are used for legitimate purposes and do not give unfair advantages over other players. In conclusion, simulating mouse clicks and keyboard presses in games using C on Linux can be a powerful tool for enhancing the gaming experience and automating tasks. By understanding the process and considering the various factors involved, you can create automation scripts, macros, or complex sequences of inputs that can give you a competitive edge and make your gaming sessions more efficient. However, it's important to use simulated inputs responsibly and within the boundaries set by the game's terms of service and community guidelines. 7.3 Simulating mouse clicks and keyboard presses in productivity tools. In addition to web browsers and games, simulating mouse clicks and keyboard presses can also be useful in productivity tools. Productivity tools are software applications designed to enhance efficiency and streamline tasks in various domains such as office work, project management, and content creation. By simulating mouse clicks and keyboard presses, users can automate repetitive actions, perform batch operations, and improve overall productivity. Automating repetitive tasks. One of the primary use cases for simulating mouse clicks and keyboard presses in productivity tools is automating repetitive tasks. Many productivity tools offer a wide range of features and functionalities, but users often find themselves performing the same actions repeatedly. For example, in a spreadsheet application, users may need to copy and paste data from one cell to another multiple times. By simulating mouse clicks and keyboard presses, users can automate these repetitive tasks, saving time and effort. Automation can be achieved by writing scripts or macros that simulate the required mouse clicks and keyboard presses. These scripts can be executed within the productivity tool itself or through external automation frameworks. For example, in a text editor, users can create a macro that automatically formats a document by applying specific styles, inserting headers and footers, and performing other formatting tasks. By assigning the macro to a keyboard shortcut, users can quickly apply the desired formatting with a single key press. Batch operations. Simulating mouse clicks and keyboard presses can also be beneficial for performing batch operations in productivity tools. Batch operations involve applying the same action to multiple files or objects simultaneously. For example, in a graphic design application, users may need to resize a batch of images to a specific dimension. Instead of manually opening each image and resizing it individually, users can write a script that simulates the necessary mouse clicks and keyboard presses to automate the resizing process. Batch operations can significantly improve productivity, especially when dealing with large datasets or complex tasks. By automating repetitive actions across multiple files or objects, users can save time and ensure consistency in their work. Productivity tools often provide scripting or automation capabilities that allow users to create custom scripts or utilize pre-built automation features to perform batch operations efficiently. Customizing workflows. Simulating mouse clicks and keyboard presses in productivity tools can also be used to customize workflows and streamline specific tasks. Each user may have unique requirements and preferences when working with productivity tools. Simulating mouse clicks and keyboard presses allows users to tailor the software to their specific needs, making their workflow more efficient and intuitive. For example, in a project management tool, users may want to assign a specific keyboard shortcut to create a new task or mark a task as complete. By simulating the required keyboard presses, users can customize the tool to match their preferred workflow. This customization can significantly improve productivity by reducing the time and effort required to perform common actions. Integration with external tools. Productivity tools often need to interact with external applications or services to enhance their functionality. Simulating mouse clicks and keyboard presses can facilitate this integration by automating interactions with external tools. For example, in a document management system, users may need to export documents to a specific file format for further processing in another application. By simulating mouse clicks and keyboard presses, users can automate the export process and seamlessly integrate the productivity tool with the external application. Integration with external tools can extend the capabilities of productivity tools and enable users to leverage the functionalities of other software applications. Simulating mouse clicks and keyboard presses provides a flexible and efficient way to interact with external tools, allowing users to perform complex tasks without leaving the productivity tool. In conclusion, simulating mouse clicks and keyboard presses in productivity tools can automate repetitive tasks, enable batch operations, customize workflows, and facilitate integration with external tools. By leveraging the power of automation, users can enhance their productivity, streamline their workflows, and achieve more efficient results in their daily tasks. Whether it's automating data entry in a spreadsheet, performing batch operations in a graphic design application, or customizing keyboard shortcuts in a project management tool, simulating mouse clicks and keyboard presses can significantly improve productivity in various productivity tools. 7.4 Simulating mouse clicks and keyboard presses in automation scripts. Automation scripts are powerful tools that can save time and effort by automating repetitive tasks. Simulating mouse clicks and keyboard presses in automation scripts allows you to interact with applications and perform actions programmatically. In this section, we will explore how to simulate mouse clicks and keyboard presses in automation scripts using C on Linux. Simulating mouse clicks. Simulating mouse clicks in automation scripts involves emulating the behavior of a physical mouse. This can be useful for automating tasks that require clicking on specific elements or buttons within an application. To simulate a mouse click, we need to determine the coordinates of the target element and send the appropriate signals to the operating system. In C, we can use the X11 library to interact with the X window system, which is commonly used on Linux. The X11 library provides functions for handling mouse events, including simulating mouse clicks. We can use the xTestFake button event function to generate a button press and release event at the specified coordinates. Here's an example of simulating a left mouse click at coordinates x, y. Hashtag include less than x11 xlib. H greater than hashtag include less than x11 extensions xtest. H greater than. Void simulate mouse click int x, int y. Display equals x open display null x test fake button event display. Button 1, true, current time x test fake button event display. Button 1, false, current time x flush display. X close display. In this example, we open a connection to the X server using X open display, generate a button press event using X test fake button event with the button 1 argument representing the left mouse button, generate a button release event with false as the third argument, flush the display to ensure the events are processed, and finally close the display using X close display. Simulating keyboard presses. Simulating keyboard presses in automation scripts allows us to automate tasks that involve typing or interacting with text fields. To simulate a keyboard press, we need to send the appropriate keycodes to the operating system. In C, we can use the X11 library to simulate keyboard presses. The X11 library provides functions for handling keyboard events, including simulating key presses. We can use the XTestFakeKeyEvent function to generate a key press and release event for a specific key code. Here's an example of simulating a keyboard press for the A key. Hashtag include less than X11 xlib. H greater than hashtag include less than X11 extensions xtest. H greater than. Void simulate key press int keycode. Display equals X open display null XTestFakeKeyEvent display keycode true current time XTestFakeKeyEvent display keycode false current time X flush display X close display. In this example, we open a connection to the X server using X open display, generate a key press event using XTestFakeKeyEvent with the specified keycode, generate a key release event with false as the third argument, flush the display to ensure the events are processed, and finally close the display using X close display. To determine the keycode for a specific key, you can use the XEV command line tool. Running XEV and pressing a key will display the keycode in the terminal. Combining mouse clicks and keyboard presses. Automation scripts often require a combination of mouse clicks and keyboard presses to perform complex tasks. By combining the techniques mentioned above, you can simulate a sequence of mouse clicks and keyboard presses to automate a series of actions. For example, let's say we want to automate the process of opening a web browser, navigating to a specific website, and entering a search query. We can use the simulate mouse click function to click on the browser icon, simulate keyboard presses to enter the website URL and search query, and simulate another mouse click to submit the search. Void automate web search. Simulate mouse click on browser icon. Simulate mouse click, browser icon X, browser icon Y. Simulate keyboard presses to enter website URL. Simulate key press, keycode 1, simulate key press, keycode 2. Simulate keyboard presses to enter search query. Simulate key press, keycode A, simulate key press, keycode B. Simulate mouse click to submit search. Simulate mouse click, submit button X, submit button Y. By combining the techniques of simulating mouse clicks and keyboard presses, you can create powerful automation scripts that can interact with applications and perform tasks automatically. In this section, we explored how to simulate mouse clicks and keyboard presses in automation scripts using C on Linux. We learned how to use the X11 library to interact with the X Windows system and generate mouse and keyboard events. By combining these techniques, you can automate repetitive tasks and streamline your workflow. 8. Security considerations. 8.1 Potential risks of simulating mouse clicks and keyboard presses. Simulating mouse clicks and keyboard presses can be a powerful tool for automating tasks and enhancing user interactions. However, it is important to be aware of the potential risks and security implications associated with this technique. In this section, we will discuss some of the potential risks of simulating mouse clicks and keyboard presses and how to mitigate them. Unauthorized access and malicious use. One of the main risks of simulating mouse clicks and keyboard presses is the potential for unauthorized access and malicious use. If an application or system allows simulated input without proper authentication and authorization mechanisms, it can be exploited by attackers to gain unauthorized access to sensitive information or perform malicious actions. To mitigate this risk, it is crucial to implement strong security measures such as user authentication, access control, and encryption. Only authorized users should be allowed to simulate mouse clicks and keyboard presses, and their actions should be logged and monitored for any suspicious activity. Injection of malicious code. Simulating mouse clicks and keyboard presses can also introduce the risk of injecting malicious code into a system. If an attacker can manipulate the simulated input, they may be able to execute arbitrary commands, exploit vulnerabilities, or compromise the integrity of the system. To prevent code injection, it is important to validate and sanitize the simulated input. Input validation should be performed to ensure that only expected and safe input is accepted. Additionally, using secure coding practices and regularly updating the system with security patches can help mitigate the risk of code injection. Impact on system stability and performance. Simulating mouse clicks and keyboard presses can have an impact on the stability and performance of the system. If the simulation is not properly implemented or if it generates a high volume of simulated events, it can overload the system and cause it to become unresponsive or crash. To minimize the impact on system stability and performance, it is important to optimize the simulation code and consider the limitations of the system. Throttling the rate of simulated events, implementing error handling and recovery mechanisms, and conducting thorough testing can help ensure that the simulation does not negatively affect the system. Compatibility issues. Simulating mouse clicks and keyboard presses may also encounter compatibility issues with different operating systems, applications, or hardware configurations. The behavior of simulated events may vary across platforms, and certain applications or systems may not support or respond to simulated input. To address compatibility issues, it is important to thoroughly test the simulation code on different platforms and configurations. Additionally, considering the specific requirements and limitations of the target system can help ensure that the simulation works as intended. Legal and ethical considerations. When simulating mouse clicks and keyboard presses, it is essential to consider the legal and ethical implications of the actions being performed. Simulating input in a way that violates laws, regulations, or ethical standards can lead to legal consequences and reputational damage. To mitigate legal and ethical risks, it is important to ensure that the simulated actions comply with applicable laws and regulations. Additionally, obtaining proper permissions and consents, respecting user privacy, and adhering to ethical guidelines can help ensure responsible and lawful use of simulated input. In conclusion, while simulating mouse clicks and keyboard presses can be a valuable tool, it is important to be aware of the potential risks and take appropriate measures to mitigate them. By implementing strong security measures, validating and sanitizing input, optimizing system performance, addressing compatibility issues, and considering legal and ethical considerations, the risks associated with simulating input can be minimized, allowing for safe and effective automation and user interaction. 8.2 Protecting against unauthorized simulations. Simulating mouse clicks and keyboard presses can be a powerful tool for automating tasks and enhancing user interactions. However, it is important to consider the security implications of allowing such simulations, as they can potentially be exploited by malicious actors. In this section, we will explore some strategies for protecting against unauthorized simulations and ensuring the integrity and security of your system. Limiting access to simulation functions. One of the first steps in protecting against unauthorized simulations is to limit access to the functions and APIs that enable mouse click and keyboard press simulations. By restricting access to these functions, you can ensure that only authorized users or applications can perform simulations. One way to achieve this is by implementing access controls and permissions within your application or system. For example, you can require users to authenticate themselves before they can access the simulation functions. This can be done through username and password authentication or by using more advanced authentication mechanisms such as two-factor authentication. Additionally, you can implement role-based access control (RBAC) to further restrict access to simulation functions. RBAC allows you to define different roles with different levels of access privileges. By assigning appropriate roles to users or applications, you can ensure that only authorized entities can perform simulations. Implementing input validation. Another important aspect of protecting against unauthorized simulations is to implement input validation. Input validation involves checking the input data for validity and ensuring that it meets certain criteria before processing it. By validating the input data, you can prevent malicious actors from injecting harmful or unauthorized commands into the simulation process. When simulating mouse clicks and keyboard presses, it is important to validate the input data that specifies the target coordinates or the keys to be pressed. For example, you can check if the coordinates fall within the boundaries of the screen or if the specified keys are valid keyboard keys. By implementing input validation, you can prevent unauthorized simulations that may lead to unintended consequences or security breaches. Implementing access logs and auditing. To enhance the security of your system, it is important to implement access logs and auditing mechanisms. Access logs can help you track and monitor the activities related to mouse click and keyboard press simulations. By logging information such as the user or application performing the simulation, the time of the simulation, and the specific actions taken, you can have a record of all simulation activities. Auditing the access logs can help you identify any suspicious or unauthorized simulations. By regularly reviewing the logs, you can detect any unusual patterns or activities that may indicate a security breach. Additionally, auditing can help you identify any potential vulnerabilities in your system and take appropriate measures to address them. Regular security updates and patching. To protect against unauthorized simulations, it is crucial to keep your system up to date with the latest security updates and patches. Software vulnerabilities can be exploited by malicious actors to gain unauthorized access or perform unauthorized simulations. By regularly updating your system and applying security patches, you can mitigate the risk of such exploits. It is recommended to subscribe to security mailing lists or follow security advisories from the relevant software vendors. This will ensure that you stay informed about any security vulnerabilities or patches related to the software components used for simulating mouse clicks and keyboard presses. By promptly applying the necessary updates, you can minimize the risk of unauthorized simulations. Secure development practices. Lastly, it is important to follow secure development practices when implementing the functionality for simulating mouse clicks and keyboard presses. This includes practices such as secure coding, input sanitization, and secure configuration. Secure coding involves using programming techniques that minimize the risk of security vulnerabilities, such as buffer overflows or injection attacks. Input sanitization involves validating and cleaning the input data to prevent any malicious or unauthorized commands from being executed. Secure configuration involves properly configuring the system and the simulation functions to ensure that they operate in a secure manner. By following secure development practices, you can reduce the likelihood of introducing vulnerabilities that can be exploited for unauthorized simulations. It is important to involve security experts or conduct security assessments during the development process to identify and address any potential security issues. In conclusion, protecting against unauthorized simulations is crucial to ensure the security and integrity of your system. By limiting access to simulation functions, implementing input validation, implementing access logs and auditing, applying regular security updates and patches, and following secure development practices, you can minimize the risk of unauthorized simulations and enhance the overall security of your system. 8.3 Best Practices for Secure Simulations. When simulating mouse clicks and keyboard presses in C using Linux, it is important to consider security implications. Simulated interactions can potentially be misused or exploited if not implemented securely. In this section, we will discuss some best practices to ensure secure simulations. 1. Validate user input. One of the key aspects of secure simulations is validating user input. Before simulating any mouse clicks or keyboard presses, it is crucial to validate the input to ensure it is coming from a trusted source. This can be done by implementing input validation techniques such as checking for the correct format, length, and range of input values. By validating user input, you can prevent potential security vulnerabilities such as injection attacks or unauthorized simulations. 2. Implement access controls. To protect against unauthorized simulations, it is important to implement access controls. This can be achieved by restricting the execution of simulation code to authorized users or processes. You can use Linux's file permissions and access control mechanisms to ensure that only trusted users or processes have the necessary privileges to simulate mouse clicks and keyboard presses. By implementing access controls, you can prevent malicious actors from exploiting the simulation functionality. 3. Use secure communication channels. If your simulation code communicates with external systems or applications, it is essential to use secure communication channels. This includes encrypting data transmission and using secure protocols such as HTTPS or SSH. By securing the communication channels, you can prevent eavesdropping, tampering, or unauthorized access to sensitive information exchanged during the simulation process. 4. Implement error handling and logging. Error handling and logging are crucial for secure simulations. By implementing robust error handling mechanisms, you can gracefully handle unexpected situations and prevent potential security vulnerabilities. Additionally, logging all simulation activities can help in identifying and investigating any security incidents or suspicious activities. Make sure to log relevant information such as user inputs, simulation actions, and any errors or exceptions encountered during the simulation process. 5. Regularly update and patch dependencies. When developing simulations in C using Linux, it is important to regularly update and patch any dependencies or libraries used in your code. This includes the Linux operating system, C libraries, and any third-party libraries or frameworks. Keeping your dependencies up to date ensures that you have the latest security patches and fixes, reducing the risk of potential vulnerabilities that could be exploited by attackers. 6. Implement privilege separation. To minimize the impact of potential security breaches, it is recommended to implement privilege separation in your simulation code. This involves dividing the code into different components or processes with different levels of privileges. By separating the privileged and non-privileged parts of the code, you can limit the potential damage caused by an attacker who gains unauthorized access to the simulation functionality. 7. Perform security audits and penetration testing. Regular security audits and penetration testing are essential to identify and address any security vulnerabilities in your simulation code. Conducting thorough security assessments can help uncover potential weaknesses or flaws that could be exploited by attackers. It is recommended to engage security professionals or ethical hackers to perform these audits and tests to ensure a comprehensive evaluation of your simulation code's security. 8. Follow secure coding practices. When writing simulation code in C, it is important to follow secure coding practices. This includes avoiding common security pitfalls such as buffer overflows, format string vulnerabilities, or integer overflows. By adhering to secure coding practices, you can minimize the risk of introducing security vulnerabilities into your simulation code. 9. Regularly monitor and update security measures. Security is an ongoing process, and it is important to regularly monitor and update your security measures. This includes monitoring system logs, analyzing security incidents, and applying necessary updates or patches to address any identified vulnerabilities. By staying vigilant and proactive in maintaining the security of your simulation code, you can ensure a robust and secure simulation environment. In conclusion, when simulating mouse clicks and keyboard presses in C using Linux, it is crucial to prioritize security. By following best practices such as validating user input, implementing access controls, using secure communication channels, and regularly updating security measures, you can minimize the risk of potential security vulnerabilities and ensure secure simulations. Remember that security is a continuous effort, and it is important to stay informed about the latest security trends and developments to adapt your security measures accordingly. 8.4 Auditing and monitoring simulated interactions. When simulating mouse clicks and keyboard presses in C using Linux, it is important to have mechanisms in place to audit and monitor these simulated interactions. Auditing and monitoring can help ensure the security and integrity of the simulated interactions, as well as provide valuable insights for troubleshooting and performance optimization. Why audit and monitor simulated interactions? Auditing and monitoring simulated interactions serve several purposes. Firstly, it allows you to track and record all simulated mouse clicks and keyboard presses, providing an audit trail of the actions performed. This can be useful for compliance purposes, such as ensuring that simulated interactions adhere to regulatory requirements. Secondly, auditing and monitoring can help identify any unauthorized or malicious simulations. By monitoring the patterns and frequency of simulated interactions, you can detect any abnormal or suspicious behavior. This can be particularly important in scenarios where simulated interactions are used in sensitive environments or critical systems. Furthermore, auditing and monitoring can provide valuable insights for troubleshooting. By analyzing the recorded interactions, you can identify any errors or issues that may have occurred during the simulation process. This can help in diagnosing and resolving problems, improving the overall reliability of the simulated interactions. Lastly, monitoring simulated interactions can aid in performance optimization. By analyzing the data collected during monitoring, you can identify any bottlenecks or inefficiencies in the simulation code. This can help you optimize the performance of your simulated interactions, ensuring they run smoothly and efficiently. Implementing auditing and monitoring. To implement auditing and monitoring of simulated interactions in your C program, you can utilize various techniques and tools. Here are some approaches you can consider. 1. Logging. One of the simplest ways to audit and monitor simulated interactions is by logging the relevant information. You can log details such as the type of interaction, mouse click or keyboard press, the coordinates of the click, the pressed key, and the timestamp of the interaction. By writing this information to a log file, you can easily review and analyze the recorded interactions. 2. Event tracing. Event tracing is a more advanced technique that allows you to capture and analyze low-level events in your program. By instrumenting your code with event tracing functions, you can record detailed information about each simulated interaction, including the context in which it occurred. This can provide deeper insights into the behavior of your simulated interactions and help in troubleshooting and optimization. 3. Performance profiling. Performance profiling tools can be used to monitor the performance of your simulated interactions. These tools can provide metrics such as CPU usage, memory consumption, and execution time for different parts of your code. By profiling your simulation code, you can identify any performance bottlenecks and optimize them for better efficiency. 4. Security monitoring. To monitor the security of your simulated interactions, you can implement security monitoring mechanisms. This can involve analyzing the patterns and frequency of simulated interactions to detect any suspicious or unauthorized behavior. Additionally, you can integrate security monitoring tools that specialize in detecting and preventing unauthorized simulations. Best practices for auditing and monitoring. To ensure effective auditing and monitoring of simulated interactions, consider the following best practices. Define clear logging and monitoring requirements. Determine what information needs to be logged and monitored based on your specific use case and compliance requirements. Implement secure logging mechanisms. Ensure that the log files are protected from unauthorized access and tampering. Consider encrypting the log files and restricting access to authorized personnel. Regularly review and analyze the logs. Set up a process to regularly review and analyze the recorded interactions. This can help identify any anomalies or issues that require attention. Integrate with existing monitoring systems. If your organization already has monitoring systems in place, consider integrating your simulated interactions monitoring with these systems. This can provide a centralized view of all system activities. Continuously update and improve monitoring techniques. Stay up to date with the latest auditing and monitoring techniques and tools. Regularly evaluate and enhance your monitoring mechanisms to adapt to evolving security threats and performance optimization needs. By implementing robust auditing and monitoring practices, you can ensure the security, reliability, and performance of your simulated interactions. This will help you build trust in your simulation code and enable you to effectively troubleshoot and optimize your applications. 9. Performance optimization. 9.1 Identifying performance bottlenecks. When simulating mouse clicks and keyboard presses in C using Linux, it is important to ensure that the performance of the simulation is optimized. Identifying and addressing performance bottlenecks is crucial to ensure smooth and efficient execution of the simulated interactions. In this section, we will explore various techniques and tools that can help in identifying performance bottlenecks in your simulation code. Profiling tools. Profiling tools are essential for analyzing the performance of your code and identifying areas that may be causing bottlenecks. These tools provide detailed information about the execution time of different functions and can help pinpoint areas that require optimization. One popular profiling tool for C programs on Linux is gprofessor. gprofessor is a command line tool that generates a profile of the time spent in each function of your program. It provides information about the number of times each function is called, the time spent in each function, and the percentage of the total execution time spent in each function. By analyzing the output of gprofessor, you can identify functions that consume a significant amount of time and focus on optimizing them. To use gprofessor, you need to compile your code with the PG flag to enable profiling information. For example, gccpgo my_program C. After running your program, you can generate the profiling report using the following command. gprofessor my_program gmon.out greater than profile.txt. The generated profile.txt file will contain detailed information about the execution time of each function in your program. Benchmarking. Benchmarking is another useful technique for identifying performance bottlenecks. By measuring the execution time of different parts of your code, you can identify areas that may require optimization. One common approach is to use the clock function from the less than time, h greater than library to measure the time taken by specific sections of your code. Here's an example of how you can use clock for benchmarking. Hashtag include less than Saintio, h greater than hashtag include less than time, h greater than. Int main. Clock underscore t start, end, double CPU underscore time underscore used. Start equals clock. Code to be benchmarked. End equals clock. CPU underscore time underscore used equals double, end, start clocks underscore per underscore sec. Printf time taken, %f seconds n, CPU underscore time underscore used. Return 0. By placing the code you want to benchmark between the start and end calls, you can measure the execution time of that specific section. Repeat the benchmarking process for different parts of your code to identify areas that may be causing performance issues. Code review and optimization. Performing a thorough code review can also help in identifying potential performance bottlenecks. Look for areas where unnecessary computations or redundant operations are being performed. Consider optimizing loops, reducing memory allocations, and minimizing disk I/O operations. Some common optimization techniques include loop unrolling. Instead of executing a loop multiple times, you can manually duplicate the loop body to reduce the overhead of loop control. Memory reuse. Reusing memory instead of allocating and deallocating it frequently can improve performance. Algorithmic improvements. Analyze your algorithms and data structures to identify opportunities for optimization. Sometimes, a different algorithm or data structure can significantly improve performance. Load testing. Load testing involves subjecting your simulation code to a high volume of simulated interactions to evaluate its performance under stress. By simulating a large number of mouse clicks and keyboard presses, you can identify how your code handles the increased load and whether it exhibits any performance issues. Load testing can be done using various tools and frameworks, such as Apache JMeter or Siege. These tools allow you to simulate a high number of concurrent users and monitor the performance of your code under different load conditions. By analyzing the results of load testing, you can identify areas that require optimization to handle the increased load more efficiently. Conclusion. Identifying performance bottlenecks is crucial when simulating mouse clicks and keyboard presses in C using Linux. Profiling tools like gprofessor, benchmarking techniques, code review, and load testing can help in identifying areas that require optimization. By addressing these bottlenecks, you can ensure that your simulation code performs efficiently and provides a smooth user experience. 9.2 Optimizing mouse click simulations. When simulating mouse clicks in C using Linux, it is important to optimize the code to ensure efficient and smooth execution. Optimizing mouse click simulations can help improve the overall performance of your application and provide a better user experience. In this section, we will explore some techniques to optimize mouse click simulations in C on Linux. 1. Minimize system calls. One way to optimize mouse click simulations is to minimize the number of system calls made during the simulation process. System calls can be expensive in terms of performance, so reducing their usage can significantly improve the efficiency of your code. Instead of making individual system calls for each mouse click, you can batch multiple mouse clicks together and send them as a single event. This can be achieved by using the write function to write multiple events to the input device file in a single call. By reducing the number of system calls, you can minimize the overhead associated with context switching and improve the overall performance of your mouse click simulations. 2. Use asynchronous I/O. Another technique to optimize mouse click simulations is to use asynchronous I/O. Asynchronous I/O allows your program to perform other tasks while waiting for input-output operations to complete. By utilizing asynchronous I/O, you can avoid blocking the execution of your program and improve its responsiveness. In Linux, you can use the epoll system call to implement asynchronous I/O. By registering the input device file descriptor with epoll and monitoring it for events, you can handle mouse click simulations asynchronously. This approach allows your program to continue executing other tasks while waiting for mouse click events, resulting in improved performance and responsiveness. 3. Implement event caching. Event caching is a technique that involves storing mouse click events in a buffer and processing them in batches. Instead of processing each mouse click event immediately, you can accumulate multiple events in a buffer and process them together at regular intervals. By implementing event caching, you can reduce the overhead associated with processing individual mouse click events. This can be particularly useful when simulating a large number of mouse clicks in a short period of time. By processing events in batches, you can minimize the number of function calls and system calls, resulting in improved performance. 4. Optimize mouse movement. In addition to simulating mouse clicks, mouse movement is an integral part of many applications. Optimizing mouse movement can further enhance the performance of your mouse click simulations. When simulating mouse movement, it is important to minimize unnecessary movements and ensure smooth transitions between positions. Instead of simulating each intermediate position between 2 points, you can calculate the direction and distance between the start and end points and simulate the movement accordingly. This approach can reduce the number of mouse movement events generated and improve the efficiency of your mouse click simulations. 5. Profile and benchmark. To identify potential bottlenecks and areas for optimization, it is essential to profile and benchmark your mouse click simulations. Profiling allows you to analyze the performance of your code and identify areas that consume excessive resources or exhibit poor performance. Benchmarking, on the other hand, helps you compare different optimization techniques and measure their impact on the overall performance of your application. By profiling and benchmarking your code, you can gain insights into the areas that require optimization and evaluate the effectiveness of different optimization strategies. This iterative process can help you fine-tune your mouse click simulations and achieve optimal performance. In conclusion, optimizing mouse click simulations in C using Linux can significantly improve the performance and responsiveness of your application. By minimizing system calls, utilizing asynchronous I/O, implementing event caching, optimizing mouse movement, and profiling your code, you can enhance the efficiency of your mouse click simulations and provide a better user experience. 9.3 Optimizing keyboard press simulations. Simulating keyboard presses in C using Linux can be a powerful tool for automating tasks and enhancing user interactions. However, as with any simulation, there are considerations for optimizing the performance of keyboard press simulations. In this section, we will explore some techniques to optimize keyboard press simulations and improve the overall efficiency of your application. 1. Minimize system calls. One of the key factors in optimizing keyboard press simulations is to minimize the number of system calls made during the simulation process. System calls involve transitioning from user space to kernel space, which can introduce overhead and impact performance. To minimize system calls, you can batch multiple keyboard press simulations together and send them as a single input event. This reduces the number of context switches between user space and kernel space, resulting in improved performance. 2. Use non-blocking I/O. By default, keyboard input is typically handled using blocking I/O operations, which means that the program waits for user input before proceeding. However, in the context of simulating keyboard presses, this can introduce delays and impact performance. To overcome this, you can use non-blocking I/O operations, which allow your program to continue executing while waiting for keyboard input. This can significantly improve the responsiveness and efficiency of your keyboard press simulations. 3. Buffer input events. Buffering input events can also help optimize keyboard press simulations. Instead of sending each keyboard press event individually, you can collect multiple events and send them as a batch. This reduces the overhead of sending individual events and can improve the overall performance of your simulation. Additionally, buffering input events allows you to control the rate at which events are sent, which can be useful in scenarios where precise timing is required. 4. Use direct input methods. Another technique to optimize keyboard press simulations is to use direct input methods provided by the operating system or input libraries. These methods bypass the standard input-output streams and directly interact with the underlying input devices. By eliminating unnecessary layers of abstraction, direct input methods can improve the efficiency and speed of keyboard press simulations. 5. Optimize key combination simulations. Simulating key combinations, such as Ctrl+C or Alt+Tab, can be more complex than simulating single key presses. To optimize key combination simulations, you can use bitwise operations to set the appropriate modifier flags and key codes. This allows you to send the combination as a single input event, reducing the overhead of sending multiple events. Additionally, you can cache the modifier flags and reuse them for subsequent key combination simulations, further improving performance. 6. Consider multi-threading. If your application involves complex keyboard press simulations or requires simultaneous input from multiple sources, you may consider using multi-threading to optimize performance. By distributing the workload across multiple threads, you can parallelize the simulation process and improve overall efficiency. However, it's important to ensure proper synchronization and thread safety to avoid race conditions and other concurrency issues. 7. Profile and benchmark. To identify potential performance bottlenecks and optimize your keyboard press simulations, it's essential to profile and benchmark your code. Profiling tools can help you identify areas of your code that consume the most resources or take the longest to execute. By focusing on these areas, you can apply targeted optimizations and improve the overall performance of your application. Benchmarking allows you to compare different approaches and measure the impact of optimizations, helping you make informed decisions about the most effective strategies. In conclusion, optimizing keyboard press simulations in C using Linux involves minimizing system calls, using non-blocking I/O, buffering input events, utilizing direct input methods, optimizing key combination simulations, considering multi-threading, and profiling and benchmarking your code. By applying these techniques, you can enhance the efficiency and responsiveness of your keyboard press simulations, resulting in a more optimized and performant application. 9.4 Benchmarking and profiling techniques. Benchmarking and profiling are essential techniques for evaluating the performance of software applications, including those that simulate mouse clicks and keyboard presses. By measuring and analyzing various aspects of the simulation process, developers can identify bottlenecks, optimize code, and improve overall efficiency. In this section, we will explore different benchmarking and profiling techniques that can be applied to simulate mouse clicks and keyboard presses in C using Linux. 9.4.1 Introduction to Benchmarking. Benchmarking involves measuring the performance of a system or component against a set of predefined criteria. In the context of simulating mouse clicks and keyboard presses, benchmarking helps developers understand how efficiently the simulation code executes and how it compares to other implementations or previous versions. By establishing a baseline performance measurement, developers can track improvements and identify areas for optimization. To benchmark a simulation, developers typically measure the time it takes to execute a specific set of actions, such as simulating a series of mouse clicks or keyboard presses. The execution time can be measured using various techniques, including manual timing, system timers, or specialized benchmarking tools. 9.4.2 Manual timing. Manual timing involves using code instrumentation to measure the execution time of specific sections of the simulation code. This technique requires developers to insert timing code before and after the code segment they want to measure. By subtracting the start time from the end time, developers can calculate the elapsed time. Here's an example of how manual timing can be implemented in C. Hashtag include less than Saintio. H greater than hashtag include less than time. H greater than. Int main. Clock underscore T start. End. Double CPU underscore time underscore used. Start equals clock. Code segment to measure. End equals clock. CPU underscore time underscore used equals double end, start clocks underscore per underscore sec. Printf execution time, %f seconds n, CPU underscore time underscore used. Return 0. In this example, the clock function from the time H library is used to measure the CPU time consumed by the code segment between the start and end timestamps. The clocks underscore per underscore sec constant is used to convert the CPU time to seconds. 9.4.3 System timers. Linux provides various system timers that can be used to measure the execution time of a program. These timers offer higher precision than the clock function and can be accessed through system calls or library functions. One commonly used system timer is the getTimeOfDay function, which returns the current time in microseconds. By capturing the time before and after the code segment, developers can calculate the elapsed time. Here's an example of how to use the getTimeOfDay function for benchmarking in C. Hashtag include less than Saintio. H greater than hashtag include less than sys time. H greater than. Int main. Struct timeEval start, end, long seconds, microseconds. Get time of day and start, null. Code segment to measure. Get time of day and end, null. Seconds equals end.tv underscore sec, start.tv underscore sec, microseconds equals end.tv underscore usec, start.tv underscore usec, double elapsed equals seconds plus microseconds 1,000,000. Printf execution time, %f seconds n, elapsed. Return 0. In this example, the getTimeOfDay function is used to capture the start and end timestamps. The difference between the timestamps is calculated to obtain the elapsed time in seconds. 9.4.4 Profiling tools. Profiling tools provide more detailed insights into the performance of a program by analyzing its execution at a finer level. These tools can identify hotspots, memory leaks, and other performance issues that may not be apparent through manual timing or system timers. One popular profiling tool for Linux is gprofessor, which is part of the new compiler collection GCC. gprofessor analyzes the execution of a program and generates a report that shows the time spent in each function and the number of times each function is called. This information helps developers identify performance bottlenecks and optimize critical sections of the code. To use gprofessor, the program must be compiled with the PG flag to enable profiling information. After running the program, the profiling data can be generated by executing the gprofessor command followed by the program's executable file. Another useful profiling tool is perf, which is a performance analysis tool provided by the Linux kernel. Perf can measure various aspects of program execution, including CPU usage, cache misses, and instruction counts. It provides detailed reports and can be used to identify performance issues at a system-wide level. To use perf, the program must be executed with the perf command followed by the program's executable file. The perf tool will collect performance data during the program's execution and generate a report once the program terminates. 9.4.5 Interpreting benchmarking and profiling results. Benchmarking and profiling techniques provide valuable data for optimizing the performance of simulations that involve mouse clicks and keyboard presses. However, interpreting the results requires careful analysis and understanding of the simulation code. When analyzing benchmarking results, developers should focus on identifying the sections of code that consume the most time. These sections are potential candidates for optimization. Profiling tools like gprofessor and perf can help pinpoint these hotspots and guide developers in optimizing the code. It's important to note that benchmarking and profiling should be performed on representative test cases that mimic real-world scenarios. Simulating a variety of mouse clicks and keyboard presses can help identify performance issues that may not be apparent in simpler test cases. By combining benchmarking, profiling, and optimization techniques, developers can enhance the performance of their simulations and create more efficient and responsive applications. Conclusion. Benchmarking and profiling techniques play a crucial role in optimizing the performance of software applications that simulate mouse clicks and keyboard presses. By measuring execution times, identifying bottlenecks, and analyzing performance data, developers can improve the efficiency and responsiveness of their simulations. Manual timing, system timers, and profiling tools like gprofessor and perf are valuable tools for benchmarking and profiling simulations in C using Linux. By applying these techniques and interpreting the results, developers can create high-performance applications that accurately simulate user interactions. 10. Real-world applications and use cases. 10.1 Automating repetitive tasks. Automating repetitive tasks is one of the key applications of simulating mouse clicks and keyboard presses in C using Linux. Many tasks in our daily lives involve performing the same actions over and over again, such as filling out forms, navigating through menus, or interacting with applications. These tasks can be time-consuming and tedious, but with the power of automation, we can save valuable time and effort. By simulating mouse clicks and keyboard presses, we can create programs that automate these repetitive tasks. With the ability to control the mouse and keyboard programmatically, we can replicate human interactions with the computer, allowing us to perform tasks automatically without any manual intervention. One common example of automating repetitive tasks is automating data entry. Imagine having to enter the same set of data into a form multiple times. Instead of manually typing the data each time, we can write a program that simulates the keyboard presses to enter the data automatically. This not only saves time but also reduces the chances of human error. Another use case for automating repetitive tasks is in the field of testing. Software testing often involves performing a series of predefined actions to verify the functionality of an application. By simulating mouse clicks and keyboard presses, we can automate the testing process, allowing us to run tests repeatedly and consistently. This helps in identifying bugs and ensuring the quality of the software. Automation can also be applied to tasks such as file management, data processing, and report generation. For example, we can write a program that automatically renames a batch of files based on certain criteria, or a program that processes a large dataset and generates reports without manual intervention. These tasks can be time-consuming if done manually, but with automation, they can be completed quickly and efficiently. One important aspect of automating repetitive tasks is the ability to handle different scenarios and conditions. For example, if a task involves interacting with a GUI application, we need to consider the various states and responses of the application. We may need to wait for certain elements to appear on the screen before performing an action, or handle error messages that may occur during the automation process. By incorporating error handling and condition checking in our automation programs, we can ensure that the tasks are completed successfully even in complex scenarios. In addition to saving time and effort, automating repetitive tasks also allows us to focus on more important and creative aspects of our work. By delegating repetitive tasks to automation, we can free up our time to work on tasks that require critical thinking, problem solving, and innovation. This not only increases productivity but also enhances job satisfaction and overall work-life balance. In conclusion, automating repetitive tasks using simulated mouse clicks and keyboard presses in C using Linux is a powerful technique that can save time, reduce errors, and increase productivity. Whether it is automating data entry, testing software, or performing file management tasks, automation allows us to complete repetitive tasks quickly and efficiently. By leveraging the capabilities of simulating mouse clicks and keyboard presses, we can automate a wide range of tasks and focus on more important aspects of our work. 10.2 Testing user interfaces. Testing user interfaces is an essential part of software development. It ensures that the application behaves as expected and provides a seamless user experience. Simulating mouse clicks and keyboard presses in C using Linux can be a powerful tool for testing user interfaces. In this section, we will explore how simulating user interactions can be used to test and validate user interfaces. Why test user interfaces? User interfaces are the primary means through which users interact with software applications. It is crucial to ensure that the user interface is intuitive, responsive, and error-free. Testing user interfaces helps identify and fix any issues or bugs that may affect the user experience. By simulating mouse clicks and keyboard presses, we can automate the testing process and perform repetitive tasks efficiently. Benefits of simulating user interactions. Simulating user interactions offers several benefits when testing user interfaces. Let's explore some of the key advantages. Automation. Simulating mouse clicks and keyboard presses allows for the automation of repetitive tasks. This saves time and effort, especially when testing complex user interfaces with multiple interactions. Consistency. Manual testing can be prone to human error and inconsistency. Simulating user interactions ensures that the same actions are performed consistently, leading to more reliable test results. Repeatability. Simulated interactions can be easily repeated, allowing for regression testing. This ensures that any changes or updates to the user interface do not introduce new issues or break existing functionality. Scalability. Simulating user interactions can be easily scaled to test various scenarios and edge cases. It enables testing across different screen resolutions, input devices, and operating systems, ensuring compatibility and responsiveness. Efficiency. Simulating user interactions can significantly speed up the testing process. It allows for the execution of multiple test cases simultaneously, reducing the overall testing time and increasing productivity. Simulating mouse clicks and keyboard presses for UI testing. Simulating mouse clicks and keyboard presses in C using Linux involves utilizing libraries and functions that interact with the X window system, which is the windowing system used by most Linux distributions. The X window system provides a set of functions that allow us to simulate user interactions programmatically. To simulate mouse clicks, we can use functions such as xTestFakeButtonEvent and xTestFakeMotionEvent. These functions allow us to generate events for left, right, and middle mouse buttons, as well as mouse movement. By specifying the desired coordinates, we can simulate mouse clicks at specific locations on the screen. Simulating keyboard presses can be achieved using functions like xTestFakeKeyEvent. This function allows us to generate key events for individual keys or key combinations. We can simulate single key presses, such as pressing the Enter key, or complex key combinations, like Ctrl+C or Shift+Tab. By combining these functions, we can create test scripts that simulate a series of user interactions, such as clicking buttons, entering text, and navigating through menus. These scripts can be executed automatically, allowing for comprehensive testing of the user interface. Best practices for UI testing with simulated interactions. When testing user interfaces using simulated interactions, it is essential to follow some best practices to ensure effective and accurate testing. Test coverage. Identify critical user interface elements and interactions that need to be tested. Focus on testing the most frequently used features and scenarios to ensure comprehensive coverage. Test data. Use a variety of test data to validate different input scenarios. Test with both valid and invalid inputs to ensure proper error handling and validation. Error handling. Implement error handling mechanisms to capture and report any errors or exceptions that occur during the testing process. This helps in identifying and resolving issues promptly. Test environment. Set up a consistent and controlled test environment to eliminate external factors that may affect the test results. Ensure that the test environment closely resembles the production environment. Test reporting. Implement a reporting mechanism to capture and document the test results. This helps in tracking the progress of testing and provides a record of the tests performed. Test maintenance. Regularly review and update the test scripts to accommodate any changes or updates to the user interface. This ensures that the tests remain relevant and effective. Simulating mouse clicks and keyboard presses in C using Linux provides a powerful tool for testing user interfaces. By automating user interactions, we can efficiently test and validate the behavior of the application's user interface. Following best practices and guidelines ensures accurate and reliable testing, leading to a better user experience and improved software quality. 10.3 Creating virtual user interactions. Creating virtual user interactions is a powerful capability that allows developers to automate tasks, test user interfaces, enhance accessibility, and perform various other tasks in a simulated environment. By simulating mouse clicks and keyboard presses in C using Linux, developers can create virtual user interactions that mimic real user actions. In this section, we will explore the techniques and tools available for creating virtual user interactions in a Linux environment. Simulating mouse clicks. Simulating mouse clicks is an essential aspect of creating virtual user interactions. By emulating mouse events, developers can automate tasks that involve clicking on buttons, selecting options from menus, and interacting with graphical user interfaces. In C, simulating mouse clicks can be achieved using the X11 library, which provides functions for manipulating the X window system. To simulate a mouse click, developers need to determine the target window and the coordinates of the click. The X11 library provides functions to retrieve information about windows and their properties. Once the target window is identified, developers can use the xtest extension to generate mouse events, such as button presses and releases, at the specified coordinates. Simulating keyboard presses. Simulating keyboard presses is another crucial aspect of creating virtual user interactions. By emulating keyboard events, developers can automate tasks that involve typing text, navigating through menus using shortcut keys, and interacting with text-based interfaces. In C, simulating keyboard presses can be achieved using the X11 library, similar to simulating mouse clicks. To simulate a keyboard press, developers need to determine the target window and the key code corresponding to the desired key. The X11 library provides functions to retrieve information about windows and their properties, as well as functions to convert key symbols to key codes. Once the target window and key code are identified, developers can use the xtest extension to generate keyboard events, such as key presses and releases, for the specified key. Handling virtual user interactions. Once virtual user interactions are created, developers may need to handle the resulting events in their applications. This is particularly important when developing GUI applications or automation scripts that rely on simulated user actions. In C, handling virtual user interactions can be achieved using event-driven programming techniques. When a simulated mouse click or keyboard press occurs, the X window system generates corresponding events that can be captured by the application. By registering event handlers, developers can define custom logic to respond to these events. For example, in a GUI application, a mouse click event may trigger the execution of a specific function or the display of a new window. Similarly, in an automation script, a keyboard press event may initiate a sequence of actions. Testing and debugging virtual user interactions. Testing and debugging virtual user interactions is an essential part of the development process. It ensures that the simulated actions accurately mimic real user behavior and that the application responds correctly to these actions. In C, testing and debugging virtual user interactions can be achieved using various techniques and tools. One common approach is to log the generated events and compare them against the expected events. By logging the events, developers can analyze the sequence of simulated actions and verify if they match the intended behavior. Additionally, developers can use debugging tools, such as GDB, to step through the code and inspect the state of the application during the simulation. Conclusion. Creating virtual user interactions in C using Linux provides developers with a powerful toolset for automating tasks, testing user interfaces, enhancing accessibility, and performing various other tasks. By simulating mouse clicks and keyboard presses, developers can create virtual user interactions that closely resemble real user actions. The X11 library, along with the Xtest extension, offers the necessary functions and capabilities to achieve this in a Linux environment. By understanding the techniques and tools available for creating virtual user interactions, developers can leverage this capability to improve their applications and streamline their development processes. 10.4 Enhancing accessibility for users with disabilities. Accessibility is an important aspect of software development, as it ensures that individuals with disabilities can effectively use and interact with computer systems. Simulating mouse clicks and keyboard presses in C using Linux can greatly enhance accessibility for users with disabilities, providing them with alternative ways to interact with applications and perform tasks. 10.4.1 Understanding accessibility needs. Users with disabilities may face challenges in using traditional input devices such as a mouse or keyboard. Some individuals may have limited mobility or dexterity, making it difficult for them to perform precise mouse movements or press specific keys on a keyboard. Others may have visual impairments and rely on assistive technologies such as screen readers or braille displays. To address these accessibility needs, software developers can implement alternative input methods that simulate mouse clicks and keyboard presses. By providing customizable options for input, developers can empower users with disabilities to navigate through applications, interact with user interfaces, and perform tasks effectively. 10.4.2 Simulating mouse clicks for accessibility. Simulating mouse clicks can be particularly beneficial for users with limited mobility or dexterity. By mapping mouse clicks to alternative input devices such as switches or joysticks, individuals can trigger actions within an application without physically manipulating a mouse. In C using Linux, developers can utilize libraries such as xlib or libinput to simulate mouse clicks programmatically. These libraries provide functions to generate mouse events, including left, right, and middle clicks. By capturing input from alternative devices and mapping them to these functions, developers can simulate mouse clicks and enable users with disabilities to interact with applications effectively. 10.4.3 Simulating keyboard presses for accessibility. Simulating keyboard presses is another essential aspect of enhancing accessibility for users with disabilities. Individuals who have difficulty pressing specific keys on a physical keyboard can benefit from alternative input methods that simulate keyboard events. In C using Linux, developers can utilize libraries such as xlib or uinput to simulate keyboard presses programmatically. These libraries provide functions to generate key events, allowing developers to simulate single key presses, key combinations, and even text input. By mapping input from alternative devices to these functions, developers can enable users with disabilities to input text, navigate through menus, and interact with applications effectively. 10.4.4 Customizing accessibility options. To further enhance accessibility, it is crucial to provide customizable options for users with disabilities. Each individual may have unique needs and preferences when it comes to alternative input methods. By allowing users to configure the behavior of simulated mouse clicks and keyboard presses, developers can ensure that the software accommodates a wide range of accessibility requirements. In C using Linux, developers can implement configuration files or settings panels that allow users to customize the behavior of simulated input. These options can include adjusting the sensitivity of mouse clicks, remapping keyboard shortcuts, or even creating personalized macros. By providing these customization options, developers can empower users with disabilities to tailor the software to their specific needs and preferences. 10.4.5 Testing and feedback from users with disabilities. When implementing accessibility features such as simulating mouse clicks and keyboard presses, it is essential to involve users with disabilities in the testing and feedback process. By actively engaging with individuals who will benefit from these accessibility enhancements, developers can gain valuable insights into the effectiveness and usability of the implemented features. Conducting usability testing with users with disabilities can help identify any issues or challenges they may face while using the simulated input methods. Gathering feedback and incorporating it into the development process can lead to iterative improvements and a more inclusive user experience. Conclusion. Simulating mouse clicks and keyboard presses in C using Linux can significantly enhance accessibility for users with disabilities. By providing alternative input methods and customizable options, developers can empower individuals to effectively interact with applications and perform tasks. It is crucial to involve users with disabilities in the testing and feedback process to ensure that the implemented features meet their needs and preferences. By prioritizing accessibility in software development, we can create more inclusive and user-friendly applications for everyone. 11. Case studies. 11.1 Simulating mouse clicks and keyboard presses in a game. Simulating mouse clicks and keyboard presses in a game can be a powerful technique to enhance the gaming experience and automate certain actions. By simulating these inputs, you can perform complex sequences of actions with precision and speed, giving you an edge in competitive gaming or simplifying repetitive tasks. Understanding the game input system. Before we dive into simulating mouse clicks and keyboard presses in a game, it's important to understand how the game's input system works. Most games have their own input handling mechanisms that listen for user input events and trigger corresponding actions in the game world. These events can include mouse clicks, keyboard key presses, mouse movement, and more. To simulate mouse clicks and keyboard presses in a game, we need to interact with the game's input system directly. This can be achieved by using low-level techniques to inject synthetic input events into the game's input queue. Simulating mouse clicks. Simulating mouse clicks in a game involves emulating the behavior of a physical mouse click. This can be useful for automating repetitive actions or executing complex sequences of mouse clicks with precision. To simulate a mouse click, we need to generate the appropriate input events and inject them into the game's input system. In Linux, this can be achieved using the xtest extension library, which provides functions for generating synthetic mouse events. The xtest library allows us to simulate left, right, and middle mouse clicks by generating button press and release events. We can specify the target window where the events should be sent, the button to simulate, and the coordinates of the click. By combining multiple mouse click events, we can create complex sequences of clicks to perform specific actions in the game. Simulating keyboard presses. Simulating keyboard presses in a game can be useful for automating repetitive keystrokes or executing complex key combinations. By simulating keyboard input, we can trigger specific actions or perform sequences of keystrokes with precision. In Linux, simulating keyboard presses can be achieved using the xtest library. The library provides functions to generate synthetic key press and release events, allowing us to simulate individual key presses. To simulate a keyboard press, we need to specify the target window where the events should be sent and the key code corresponding to the desired key. By combining multiple key press events, we can simulate complex key combinations, such as Ctrl plus Shift plus A, to trigger specific actions in the game. Integrating simulated inputs with the game. Once we have the ability to simulate mouse clicks and keyboard presses, the next step is to integrate these simulated inputs with the game itself. This involves identifying the appropriate target window where the events should be sent and ensuring that the game's input system recognizes and responds to the simulated inputs. To identify the target window, we can use tools like XWinInfo or XDO tool to obtain information about the game window, such as its title or window ID. Once we have the target window, we can use the xtest library to inject the synthetic input events directly into the game's input queue. However, it's important to note that not all games may be receptive to simulated inputs. Some games may have built-in anti-cheat mechanisms or input validation checks that can detect and block synthetic input events. In such cases, additional techniques like hooking into the game's input handling functions may be required to bypass these checks. Best practices and considerations. When simulating mouse clicks and keyboard presses in a game, there are a few best practices and considerations to keep in mind. Respect the game's terms of service. Before simulating inputs in a game, make sure to review the game's terms of service and ensure that you are not violating any rules or policies. Test in a controlled environment. It's important to test your simulated inputs in a controlled environment to avoid unintended consequences or conflicts with other applications or processes running on your system. Avoid excessive automation. While simulating inputs can be helpful for automating repetitive tasks, it's important to avoid excessive automation that may give unfair advantages or disrupt the intended gameplay experience. Stay up to date. Game updates or patches can introduce changes to the input system or anti-cheat mechanisms. Stay informed about these updates to ensure that your simulated inputs continue to work effectively. By following these best practices and considering the specific requirements and limitations of the game you are working with, you can effectively simulate mouse clicks and keyboard presses to enhance your gaming experience or automate certain actions. 11.2 Simulating mouse clicks and keyboard presses in a web browser. Simulating mouse clicks and keyboard presses in a web browser can be a powerful tool for automating tasks, testing web applications, and enhancing user experience. In this section, we will explore how to simulate these interactions using C on a Linux platform. Simulating mouse clicks. Simulating mouse clicks in a web browser involves emulating the events triggered by a physical mouse click. These events include mouse button press, release, and movement. To simulate a mouse click, we need to identify the target element on the web page and generate the appropriate events. One approach to simulating mouse clicks is by using the X11 library, which provides a low-level interface for interacting with the X window system. With X11, we can create a connection to the X server, obtain the window ID of the web browser, and send events to simulate mouse clicks. To simulate a left mouse click, we can use the xTestFake button event function to generate a button press event followed by a button release event. We need to specify the button number, usually 1 for the left button, and the window ID of the web browser. Additionally, we can set the mouse coordinates to determine where the click should occur on the web page. Hashtag include less than x11 xlib. H greater than hashtag include less than x11 extensions xtest. H greater than. Void simulate left mouse click display window int x int y. xTestFake motion event display -1 x y 0 xTestFake button event display 1 true 0 xTestFake button event display 1 false 0 x flush display. Similarly, we can simulate right and middle mouse clicks by changing the button number in the xTestFake button event function to 3 and 2, respectively. Simulating keyboard presses. Simulating keyboard presses in a web browser involves emulating the events triggered by pressing a key on the physical keyboard. These events include key press and release. To simulate a keyboard press, we need to identify the target element on the web page and generate the appropriate events. Again, we can use the X11 library to simulate keyboard presses. The xTestFake key event function allows us to generate key press and release events. We need to specify the key code corresponding to the desired key in the window ID of the web browser. Hashtag include less than x11 xlib. H greater than hashtag include less than x11 extensions xtest. H greater than. Void simulate key press display window unsigned int keycode. xTestFake key event display keycode true 0 x flush display. Void simulate key release display window unsigned int keycode. xTestFake key event display keycode false 0 x flush display. To determine the key code for a specific key, we can use the XEV command line tool provided by X11. Running XEV and pressing a key will display the corresponding key code in the terminal. Integration with web browsers. To simulate mouse clicks and keyboard presses in a web browser, we need to obtain the window ID of the browser window. One way to achieve this is by using the xGetInputFocus function from the X11 library. This function returns the window ID of the currently focused window. Hashtag include less than x11 xlib. H greater than. Window get focused window display. Window focused window, int revert to. xGetInputFocus display, and focused window, and revert to return focused window. Once we have the window ID, we can pass it to the functions for simulating mouse clicks and keyboard presses. Limitations and considerations. Simulating mouse clicks and keyboard presses in a web browser using C on Linux has some limitations. Firstly, this approach relies on the X window system, which may not be available on all systems or may have different implementations. Therefore, it is important to ensure compatibility with the target system. Secondly, simulating interactions in a web browser may not always produce the desired results. Web pages can have complex JavaScript interactions, event listeners, and dynamic content that may not be fully replicated by simulating mouse clicks and keyboard presses alone. In such cases, it may be necessary to use additional techniques, such as injecting JavaScript code or using browser automation frameworks. Lastly, it is important to consider the security implications of simulating interactions in a web browser. Unauthorized simulations can potentially lead to security vulnerabilities or abuse of web applications. It is crucial to follow best practices for secure simulations, such as validating user input and implementing proper access controls. In conclusion, simulating mouse clicks and keyboard presses in a web browser using C on Linux can be achieved by leveraging the X11 library. By generating the appropriate events, we can automate tasks, test web applications, and enhance user experience. However, it is important to be aware of the limitations and security considerations associated with this approach. 11.3 Simulating mouse clicks and keyboard presses in a GUI application. In this section, we will explore how to simulate mouse clicks and keyboard presses in a GUI application using C on Linux. Simulating user input in a GUI application can be useful for automating tasks, testing user interfaces, or creating virtual user interactions. By simulating mouse clicks and keyboard presses, we can mimic user actions and interact with the application programmatically. Simulating mouse clicks. Simulating mouse clicks in a GUI application involves generating appropriate events that mimic the actions of a physical mouse. These events can be used to trigger actions such as button clicks, dragging, or scrolling. In C on Linux, we can use the X11 library to simulate mouse clicks. To simulate a mouse click, we need to determine the target window and the coordinates of the click. We can obtain the target window using the XOpenDisplay function, which establishes a connection to the X server. Once we have the target window, we can use the XWarp pointer function to move the mouse cursor to the desired coordinates. Finally, we can generate a button press event using the xTestFake button event function to simulate the mouse click. Here is an example code snippet that demonstrates how to simulate a left mouse click in a GUI application. Hashtag include less than x11 xlib. H greater than hashtag include less than x11 extensions x test H greater than. Void simulate mouse click display window target window int x int y. X warp pointer display none target window 0 0 0 0 x y x sync display false. X test fake button event display button 1 true current time x sync display false. X test fake button event display button 1 false current time x sync display false. Int main display equals x open display null window target window equals. Obtain the target window int x equals. Specify the x coordinate of the click int y equals. Specify the y coordinate of the click. Simulate mouse click display target window x y. X close display return 0. By modifying the button parameter in the x test fake button event function, we can simulate different mouse buttons such as the right button button 3 or the middle button button 2. Simulating keyboard presses. Simulating keyboard presses in a GUI application involves generating appropriate events that mimic the actions of a physical keyboard. These events can be used to simulate single key presses, key combinations, or even text input. In C on Linux, we can use the X11 library to simulate keyboard presses. To simulate a keyboard press, we need to determine the target window and the key code of the desired key. We can obtain the target window using the XOpenDisplay function, similar to simulating mouse clicks. Once we have the target window, we can generate a key press event using the XTestFakeKeyEvent function to simulate the keyboard press. Here is an example code snippet that demonstrates how to simulate a keyboard press in a GUI application. Hashtag include less than x11 xlib. H greater than hashtag include less than x11 extensions xtest. H greater than. Void simulate key press display window target window keycode key. XTestFakeKeyEvent display key true current time x sync display false. XTestFakeKeyEvent display key false current time x sync display false. Int main display equals XOpenDisplay null window target window equals. Obtain the target window keycode key equals. Specify the key code of the desired key. Simulate key press display target window key. X close display return 0. To determine the key code of a specific key, you can use the XEV command line tool, which displays X events. Run the XEV tool and press the desired key to obtain its key code. Handling mouse and keyboard events in a GUI application. In a GUI application, it is also important to handle mouse and keyboard events generated by the user. By capturing and processing these events, we can respond to user interactions and perform appropriate actions. To handle mouse events, we can use the X11 library to register event handlers for button presses, button releases, and mouse motion. These event handlers can be used to trigger specific actions based on the user's mouse interactions. To handle keyboard events, we can use the X11 library to register event handlers for key presses and key releases. These event handlers can be used to capture user input and perform actions based on the pressed keys. By combining the ability to simulate mouse clicks and keyboard presses with the capability to handle user-generated events, we can create powerful GUI applications that can both respond to user interactions and simulate user actions programmatically. In the next section, we will explore how to simulate mouse clicks and keyboard presses in an automation script. 11.4 Simulating mouse clicks and keyboard presses in an automation script. In this section, we will explore how to simulate mouse clicks and keyboard presses in an automation script using C on Linux. Automation scripts are powerful tools that can automate repetitive tasks, improve efficiency, and reduce human error. By simulating mouse clicks and keyboard presses, we can create scripts that interact with graphical user interfaces, GUIs, and perform actions on behalf of the user. Simulating mouse clicks. Simulating mouse clicks in an automation script involves sending appropriate signals to the operating system to mimic the behavior of a physical mouse click. In C, we can achieve this by utilizing the X11 library, which provides functions for interacting with the X window system, the standard windowing system on Linux. To simulate a mouse click, we need to specify the coordinates of the target location on the screen. We can obtain the screen coordinates using the X11 library's functions. Once we have the coordinates, we can use the XTestFakeButtonEvent function to generate a button press and release event at the specified location. Here's an example code snippet that demonstrates how to simulate a left mouse click. Hashtag include less than x11 xlib. H greater than hashtag include less than x11 extensions xtest. H greater than. Void simulate left mouse click int x int y. Display equals XOpenDisplay null XTestFakeButtonEvent display. Button 1 true current time XTestFakeButtonEvent display. Button 1 false current time XFlush display. X close display. Int main. Simulate left mouse click 100 return 0. In this example, the simulate left mouse click function takes the x and y coordinates of the target location as parameters. It opens a connection to the X server using XOpenDisplay, generates a button press event using xTestFake button event with the button 1 argument representing the left mouse button, generates a button release event, flushes the events to the server using xFlush, and finally closes the display connection using xClose display. Simulating keyboard presses. Simulating keyboard presses in an automation script involves sending appropriate keycodes to the operating system to mimic the behavior of a physical key press. Again, we can utilize the X11 library in C to achieve this. To simulate a keyboard press, we need to specify the keycode of the target key. The X11 library provides a function called xTestFakeKeyEvent that allows us to generate key press and release events. We can use the xKeySym to keycode function to convert a key symbol, e.g., A, enter, F1 foot to its corresponding keycode. Here's an example code snippet that demonstrates how to simulate a key press. Hashtag include less than x11 xlib. H greater than hashtag include less than x11 extensions xtest. H greater than. Void simulate key press char key. Display equals x open display null keycode equals x keysym to keycode display. Key xTestFakeKeyEvent display. Keycode true current time x flush display. X close display. Int main. Simulate key press A, return 0. In this example, the simulate key press function takes a character representing the target key as a parameter. It opens a connection to the X server, converts the key symbol to its corresponding keycode using xKeysym to keycode, generates a key press event using xTestFakeKeyEvent, flushes the event to the server, and finally closes the display connection. Combining mouse clicks and keyboard presses. In an automation script, it is often necessary to combine mouse clicks and keyboard presses to perform complex actions. For example, you may need to click on a specific button and then enter text into a text field. By combining the techniques discussed above, you can easily achieve this. Here's an example code snippet that demonstrates how to simulate a mouse click followed by a keyboard press. Hashtag include less than x11 xlib. H greater than hashtag include less than x11 extensions xtest. H greater than. Void simulate mouse click and key press int x, int y, char key. Display equals x open display null xTestFake button event display. Button 1, true, current time xTestFake button event display. Button 1, false, current time keycode equals x keysym to keycode display. Key xTestFakeKeyEvent display. Keycode, true, current time x flush display. X close display. Int main. Simulate mouse click and key press 100, A, return 0. In this example, the simulate mouse click and key press function takes the x and y coordinates of the target location and the character representing the target key as parameters. It opens a connection to the X server, generates a mouse click event, converts the key symbol to its corresponding keycode, generates a key press event, flushes the events to the server, and finally closes the display connection. By combining these techniques, you can create powerful automation scripts that can interact with GUI applications, perform complex actions, and streamline your workflow. In this section, we explored how to simulate mouse clicks and keyboard presses in an automation script using C on Linux. We learned how to use the X11 library to generate mouse click and keyboard press events, and how to combine these events to perform complex actions. With this knowledge, you can now create automation scripts that can interact with GUI applications and automate repetitive tasks efficiently. 12. Conclusion. 12.1 Summary of key concepts. In this book, we have explored the world of simulating mouse clicks and keyboard presses in C using Linux. We have covered a wide range of topics, from understanding mouse and keyboard events to advanced techniques for simulating interactions. In this final section, we will summarize the key concepts discussed throughout the book and provide some final thoughts and recommendations. Throughout the chapters, we have learned about the importance of simulating mouse clicks and keyboard presses in various scenarios. Whether it is automating repetitive tasks, testing user interfaces, creating virtual user interactions, or enhancing accessibility for users with disabilities, simulating these interactions can greatly improve efficiency and productivity. We started by introducing the basics of simulating mouse clicks and keyboard presses, including an overview of the benefits and prerequisites for this process. We also discussed how to set up the development environment in Linux, ensuring that we have the necessary tools and libraries to proceed. Next, we delved into simulating mouse clicks, exploring different types of mouse events such as left, right, and middle clicks. We learned how to simulate these events using C code, allowing us to interact with graphical user interfaces and perform actions programmatically. Following that, we shifted our focus to simulating keyboard presses. We discussed the different types of keyboard events, including single key presses, key combinations, and text input. We explored how to simulate these events using C code, enabling us to automate text input and execute complex keyboard shortcuts. In the subsequent chapters, we explored how to handle mouse and keyboard events in both GUI and console applications. We learned how to capture these events and respond to them accordingly, allowing us to create interactive applications that respond to user input. We then delved into advanced techniques for simulating mouse clicks and keyboard presses. We discussed how to simulate mouse movement, dragging, scrolling, and even keyboard macros. These techniques provide us with more flexibility and control over our simulated interactions, allowing us to create more realistic and complex simulations. In the chapter on error handling and troubleshooting, we explored common errors and issues that may arise during the simulation process. We discussed various debugging techniques, logging, and error reporting strategies to help us identify and resolve any problems that may occur. Integration with other applications was another important aspect we covered. We explored how to simulate mouse clicks and keyboard presses in web browsers, games, productivity tools, and automation scripts. This integration allows us to extend the functionality of these applications and automate various tasks. We also discussed security considerations when simulating mouse clicks and keyboard presses. We explored potential risks and ways to protect against unauthorized simulations. We emphasized the importance of following best practices for secure simulations and auditing and monitoring simulated interactions. Performance optimization was another crucial topic we covered. We discussed how to identify performance bottlenecks and optimize mouse click and keyboard press simulations. We explored benchmarking and profiling techniques to ensure that our simulations run efficiently and smoothly. In the chapter on real-world applications and use cases, we explored various scenarios where simulating mouse clicks and keyboard presses can be beneficial. From automating repetitive tasks to testing user interfaces and enhancing accessibility, we discussed how these simulations can be applied in practical situations. Finally, in the case studies chapter, we examined specific examples of simulating mouse clicks and keyboard presses in different contexts, such as games, web browsers, GUI applications, and automation scripts. These case studies provided us with real-world examples and insights into how these simulations can be implemented effectively. In conclusion, this book has provided a comprehensive guide to simulating mouse clicks and keyboard presses in C using Linux. We have covered a wide range of topics, from the basics to advanced techniques, and explored various applications and use cases. By understanding and implementing these concepts, readers can harness the power of simulating interactions to automate tasks, test applications, and enhance user experiences. As technology continues to evolve, we can expect further advancements in this field, opening up new possibilities for simulating mouse clicks and keyboard presses. 12.2 Future Trends and Developments. As technology continues to advance, the field of simulating mouse clicks and keyboard presses in C using Linux is also evolving. In this section, we will explore some of the future trends and developments that we can expect to see in this area. 1. Integration with artificial intelligence and machine learning. One of the most exciting developments in the field of simulating mouse clicks and keyboard presses is the integration with artificial intelligence (AI) and machine learning (ML) techniques. By leveraging AI and ML algorithms, we can enhance the accuracy and efficiency of simulating user interactions. For example, AI algorithms can be trained to recognize patterns in user behavior and adapt the simulated interactions accordingly. This can lead to more realistic and intelligent simulations that closely mimic human actions. ML techniques can also be used to optimize the performance of simulations by identifying and eliminating unnecessary or redundant actions. 2. Enhanced accessibility features. Simulating mouse clicks and keyboard presses can greatly enhance accessibility for users with disabilities. In the future, we can expect to see more advanced features and techniques that cater specifically to the needs of these users. For example, there could be improved support for simulating alternative input methods, such as eye tracking or voice commands. Additionally, there may be advancements in simulating complex gestures or multi-touch interactions, which can greatly benefit users with limited mobility. 3. Cross-platform compatibility. With the increasing popularity of multi-platform applications, there is a growing need for simulating mouse clicks and keyboard presses across different operating systems and devices. In the future, we can expect to see more tools and libraries that provide cross-platform compatibility. These tools will allow developers to write code that can be easily ported to different platforms, such as Windows, macOS, and mobile operating systems. This will enable the creation of more versatile and flexible simulations that can be used across a wide range of devices and environments. 4. Improved performance and efficiency. As technology advances, we can expect to see improvements in the performance and efficiency of simulating mouse clicks and keyboard presses. This includes faster response times, reduced latency, and optimized resource utilization. Advancements in hardware, such as faster processors and increased memory capacity, will contribute to improved performance. Additionally, software optimizations and algorithmic improvements will further enhance the efficiency of simulations. 5. Integration with virtual and augmented reality. Virtual reality (VR) and augmented reality (AR) technologies are becoming increasingly popular, and the integration of simulating mouse clicks and keyboard presses with these technologies holds great potential. In the future, we can expect to see tools and frameworks that enable developers to simulate user interactions in virtual and augmented reality environments. This will open up new possibilities for creating immersive and interactive experiences, such as virtual training simulations or augmented reality games. 6. Enhanced security measures. As simulating mouse clicks and keyboard presses becomes more prevalent, it is crucial to address the security concerns associated with this technology. In the future, we can expect to see enhanced security measures to protect against unauthorized simulations and ensure the integrity of user interactions. This may include the implementation of encryption techniques to secure simulated interactions, as well as the development of authentication mechanisms to verify the legitimacy of simulated actions. Additionally, there may be advancements in auditing and monitoring tools to detect and prevent malicious simulations. 7. Integration with Internet of Things (IoT) devices. The Internet of Things (IoT) is a rapidly growing field that involves connecting various devices and objects to the Internet. In the future, we can expect to see integration between simulating mouse clicks and keyboard presses and IoT devices. This integration will enable developers to simulate user interactions with IoT devices, such as smart home appliances or industrial automation systems. This opens up new possibilities for automating tasks and controlling IoT devices remotely. In conclusion, the field of simulating mouse clicks and keyboard presses in C using Linux is constantly evolving. We can expect to see future trends and developments that leverage AI and ML, enhance accessibility features, improve cross-platform compatibility, optimize performance, integrate with virtual and augmented reality, enhance security measures, and integrate with IoT devices. These advancements will further enhance the capabilities and applications of simulating user interactions, opening up new possibilities for automation, accessibility, and immersive experiences. 12.3 Final Thoughts and Recommendations. In this book, we have explored the world of simulating mouse clicks and keyboard presses in C using Linux. We have covered various topics, from understanding mouse and keyboard events to advanced techniques for simulating interactions. Now, in this final section, let's summarize the key concepts we have learned and provide some recommendations for further exploration. Summary of key concepts. Throughout this book, we have covered a wide range of topics related to simulating mouse clicks and keyboard presses in C using Linux. Here are the key concepts we have discussed. Simulating mouse clicks. We have learned how to simulate left, right, and middle mouse clicks using the X11 library in Linux. We have also explored techniques for simulating mouse movement, dragging, and scrolling. Simulating keyboard presses. We have seen how to simulate single key presses, key combinations, and text input using the X11 library. We have also discussed the importance of handling keyboard events in both GUI and console applications. Handling mouse and keyboard events. We have explored techniques for capturing and handling mouse and keyboard events in both GUI and console applications. We have seen how to integrate simulated interactions with other applications, such as web browsers, games, productivity tools, and automation scripts. Advanced techniques. We have delved into advanced techniques for simulating mouse clicks and keyboard presses, including mouse movement, dragging, scrolling, and keyboard macros. These techniques can be used to enhance the functionality and user experience of applications. Error handling and troubleshooting. We have discussed common errors and issues that may arise during the simulation process. We have also explored debugging techniques, logging, error reporting, and troubleshooting tips and tricks. Security considerations. We have examined the potential risks of simulating mouse clicks and keyboard presses and discussed ways to protect against unauthorized simulations. We have also highlighted best practices for secure simulations and the importance of auditing and monitoring simulated interactions. Performance optimization. We have learned how to identify performance bottlenecks and optimize mouse click and keyboard press simulations. We have explored benchmarking and profiling techniques to ensure efficient and smooth interactions. Real-world applications and use cases. We have discussed various real-world applications and use cases for simulating mouse clicks and keyboard presses, including automating repetitive tasks, testing user interfaces, creating virtual user interactions, and enhancing accessibility for users with disabilities. Case studies. We have presented case studies on simulating mouse clicks and keyboard presses in different scenarios, such as games, web browsers, GUI applications, and automation scripts. These case studies have provided practical examples of how to apply the concepts learned in this book. Future trends and developments. The field of simulating mouse clicks and keyboard presses is constantly evolving. As technology advances, new techniques and tools may emerge to enhance the simulation process. Here are some future trends and developments to keep an eye on. Cross-platform support. While this book focuses on simulating mouse clicks and keyboard presses in Linux using C, there is a growing demand for cross-platform solutions. Future developments may provide libraries or frameworks that allow simulating interactions on multiple operating systems. Integration with virtual reality (VR) and augmented reality (AR). As VR and AR technologies become more prevalent, there may be opportunities to simulate mouse clicks and keyboard presses in virtual and augmented environments. This could open up new possibilities for immersive user experiences. Natural language processing (NLP) integration. With the rise of voice assistants and natural language processing, there may be opportunities to simulate keyboard presses based on voice commands. This could enable more intuitive and hands-free interactions. Machine learning and AI. Machine learning and AI techniques can be leveraged to improve the accuracy and efficiency of simulating mouse clicks and keyboard presses. Future developments may incorporate these technologies to enhance the simulation process. Final thoughts and recommendations. Simulating mouse clicks and keyboard presses in C using Linux opens up a world of possibilities for developers. Whether you are automating repetitive tasks, testing user interfaces, or creating virtual user interactions, the knowledge gained from this book will serve as a solid foundation. To further explore this topic, here are some recommendations. Experiment with different libraries. While this book focuses on the X11 library, there are other libraries available for simulating mouse clicks and keyboard presses in Linux, such as the U-Input library. Experimenting with different libraries can broaden your understanding and provide alternative approaches. Explore GUI frameworks. If you are interested in developing GUI applications that involve simulating mouse clicks and keyboard presses, consider exploring GUI frameworks like GTK or Qt. These frameworks provide higher-level abstractions and tools for handling user interactions. Contribute to open-source projects. There are several open-source projects related to simulating mouse clicks and keyboard presses. Contributing to these projects can not only enhance your skills but also benefit the wider developer community. Stay updated with latest technologies. As mentioned earlier, the field of simulating mouse clicks and keyboard presses is constantly evolving. Stay updated with the latest technologies, libraries, and frameworks to keep your skills relevant and take advantage of new opportunities. In conclusion, simulating mouse clicks and keyboard presses in C using Linux is a powerful skill that can greatly enhance the functionality and user experience of applications. By understanding the key concepts, exploring advanced techniques, and staying updated with the latest developments, you can become proficient in simulating interactions and unlock a world of possibilities in software development.